Right now, as you listen to this, you're hurtling through space at over 1,000,000 miles per hour. Not because Earth is spinning beneath your feet or orbiting the sun. No, something far more massive is pulling our entire galaxy across the universe like a cosmic fishing line. Scientists call it the Great Attractor, a gravitational monster hiding behind a curtain of stars and dust so thick we cannot see through it. And it's dragging the Milky Way, Andromeda, and roughly 100,000 other galaxies toward a destination we've never laid eyes on. This shouldn't be happening. In the 1970s, astronomers discovered something that violated everything they thought they understood about the cosmos. Every galaxy near us was moving in the same direction. That's not supposed to occur. When the universe exploded into existence 13.8 billion years ago, everything scattered outward in all directions. Space itself stretched between galaxies like an expanding balloon, pushing them apart in a cosmic expansion that plays by one simple rule. The farther away a galaxy is, the faster it should be racing away from us. Confirmed, measured, the foundation of everything we know about cosmology. But the data told a different story. Astronomers measured the light from nearby galaxies, hunting for the telltale fingerprints of motion. Light stretches when objects flee. It shifts toward red. Light compresses when objects approach. It shifts toward blue. The measurements confirmed what expansion predicted, but then they looked closer. They examined the tiny deviations, the small extra velocities layered on top of the expected motion, and they saw something that made no sense. Hundreds of galaxies in our cosmic neighborhood weren't moving randomly. They weren't scattered in different directions. They were all being pulled toward the same point in space. The same direction, purposeful, coordinated. Like raindrops in a storm suddenly converging on a single spot on the horizon. Something over there had rewritten the rules. Something was pulling. The Milky Way itself was moving at over 1,000,000 miles per hour. Our entire local group of galaxies, Andromeda, dozens of smaller companions, all of us being dragged along. The Virgo cluster, a swarm of thousands of galaxies 60 million light-years away, was flowing in the same current. The Hydra Centaurus supercluster, even more distant, caught in the same invisible tide. Scientists checked their instruments. They recalculated. They measured again and again. The pattern held. Every single measurement confirmed the same unsettling truth. Something out there, something massive beyond comprehension, was reaching across unimaginable distances and pulling on everything around us. To generate gravitational force strong enough to accelerate thousands of galaxies would require a concentration of mass unlike anything humanity had ever detected. Scientists pointed their telescopes toward the source. They aimed their most powerful instruments at the region where all these cosmic currents converged. They found nothing. The exact location where this invisible monster should have been sitting was blocked, hidden behind the densest part of our own galaxy, a wall of stars, gas, and dust so thick it swallowed all the light beyond. They were trying to observe the greatest gravitational anomaly in the local universe while standing inside the very cloud that hid it. They were trying to see through their own blindfold. But the pull was real. The motion was undeniable. The mathematics didn't lie. Something was out there, invisible, yet impossible to ignore. Rewriting the rules of how galaxies should move. When astronomers needed a name for this mystery, they called it the Great Attractor. What could possibly generate such enormous gravity remains one of the deepest puzzles in astronomy today. And the problem was never just that they couldn't see it. In the 1980s, astronomers thought they had it all figured out. They'd mapped the local group. They'd charted the Virgo cluster. They understood how gravity worked on cosmic scales. They were confident. They were wrong. Then Alan Dressler and his team did something radical. They pointed their instruments outward, millions of light years into the void, and started collecting data. They measured redshift, watching how light stretches as galaxies flee from us. They calculated distances using multiple methods, cross-checking every single number. And when they combined it all together, something extraordinary emerged. The galaxies weren't moving randomly. They were organized. They were flowing, like water circling a drain, like fish swept downstream. The entire cosmic neighborhood was being pulled in one direction. The Milky Way, our galaxy, the local group, all of us were moving at 600,000 miles per hour toward a single point in the constellation Centaurus. But it got stranger. The Virgo cluster, containing over 1,000 galaxies, was flowing the same way. Galaxy clusters hundreds of millions of light years away showed the same directional pull. Something was tugging at the fabric of the universe itself. Scientists did the math. They calculated the gravitational mass needed to create this. The answer made them pause. You would need to concentrate tens of thousands of galaxies in one region. The combined mass would equal 10 million billion times the weight of our entire galaxy. Multiple independent measurements confirmed it. The gravity was real. The motion was undeniable. But the source? Completely invisible. That's where it got truly unsettling. The pull wasn't equal from all directions. Galaxies closer moved faster, exactly as gravity predicted, but the pattern was too complex for a simple point mass. The flow lines curved and twisted. They hinted at structure within structure, concentrations within concentrations. Whatever was pulling us had internal architecture, complex, intricate, completely hidden. Astronomers tried everything. Visible light couldn't penetrate the galactic dust blocking our view. Infrared revealed hints, but remained too obscured. Radio waves cut through the dust more easily, whispering of massive galaxy clusters lurking in the forbidden zone, a region of sky we simply couldn't observe properly. Every new measurement confirmed it existed. Every new observation failed to reveal what it actually was. The astronomical community fractured. Some argued it was a single supermassive structure, perhaps the largest galaxy cluster ever discovered. Others believed it was multiple clusters aligned along our line of sight, creating the illusion of one enormous concentration. A few whispered about exotic possibilities, dark matter distributions, gravitational lensing effects, things that bent the rules of what they thought was possible. None could prove anything. By the late 1980s, the Great Attractor had become astronomy's most famous ghost, an invisible giant pulling us across the cosmos at incomprehensible speeds, massive enough to influence the motion of structures spanning 1 billion light years, and completely hidden, locked behind the one region of sky we couldn't see through. The race was on to pierce the veil, but the tools didn't exist yet. The universe was keeping its secret, and we were powerless to pry it loose. Imagine standing in a river without knowing it. You feel the current pulling you downstream, but you can't see where it's going. For centuries, we thought we understood our place in the cosmos. We lived in a galaxy. That galaxy belonged to a local group. That group fell toward the Virgo cluster. Simple, neat, wrong. Then, in the early 2000s, astronomers built new tools that changed everything. They could finally measure how fast galaxies were actually moving with precision that was almost impossible before. Not just rough estimates, real numbers. The Cosmic Flows Project began its work. They didn't just point a telescope and take a measurement. Each galaxy required detective work. Scientists found specific types of stars that always shine with identical brightness, using them like cosmic light bulbs to measure distance. They watched galaxies spin and used that rotation speed to reveal their true size. They combined every technique available, building a three-dimensional map of our universe, one galaxy at a time. The work was slow. Weeks per galaxy, months of patient observation. But the data kept accumulating. Thousands of data points. Thousands of tiny arrows pointing in space, showing which direction galaxies were moving and how fast. Then something unexpected happened. Patterns emerged from the chaos. We weren't just falling toward the Virgo cluster. That was only part of the story. Our local group, the Virgo cluster itself, the Hydra Centaurus supercluster, stretching millions of light years into the void. All of it was moving together. Not randomly, not independently, all flowing in the same direction, like water spiraling down a drain. Scientists created visualizations of this cosmic current. Imagine a weather map. But instead of showing clouds and wind patterns across a continent, it showed the motion of galaxies across hundreds of millions of light years. Red zones marked the fastest moving regions. Blue zones showed slower drift. Streamlines traced the paths. Galaxies followed as they fell through space. And at the center of it all sat the Great Attractor, a red-hot convergence point where all the paths led. But then came the real shock. The flow didn't stop there. The streamlines continued beyond the Great Attractor, stretching even farther into the unknown. Some galaxies near the Great Attractor moved faster than its gravity alone could explain. Something bigger was pulling from beyond. The cosmic river didn't empty into a single ocean. It was tributaries feeding into a vastly larger river system. And that system flowed toward structures we hadn't even discovered yet. Think of it this way. You're hiking through a forest and find a small creek. You follow it downstream. Sure, it leads to a pond. Instead, the creek merges into a river. Then that river joins an even bigger river. The scale keeps expanding, again and again, until you realize you never understood how large the system actually was. Now apply that to the cosmos. Galaxies 300 million light years away were caught in the same current. 300 million light years. The light from those galaxies took 300 million years to reach Earth. We're seeing them as they existed when dinosaurs first walked the planet. Yet even then, billions of years ago, they were already flowing in coordinated paths toward the same gravitational basin. The data told a story that should have been impossible. According to our models of the universe, there simply wasn't enough time since the Big Bang for gravity to organize matter into a structure this enormous. The universe is only 13.8 billion years old. Gravity is slow. It should take far longer to build something this vast. Yet here was the evidence. Measured, confirmed, repeated across thousands of independent data points. The Great Attractor wasn't the final answer. It was just the first layer of a mystery that went deeper and deeper, larger and larger. But there's a problem. The region that contains the Great Attractor has a name among astronomers: the zone of avoidance. It sounds mysterious. It sounds like some exotic cosmic barrier or a phenomenon we don't understand. The truth is far simpler and far more frustrating. It's just dust, just gas, just stars from our own galaxy blocking our view like a wall we can never see around. Our Milky Way galaxy sits between us and the structure that's pulling us through space. And this zone of dust and obscuration covers roughly 20% of the entire sky we can observe from Earth. We're staring at the hand that's pulling us, but we can't quite see it. We can only see its effects. We can only measure where it's dragging us and wonder what lies hidden in the cosmic river source. The universe's greatest hidden mystery. Here's the thing about our cosmic neighborhood. We're basically living inside a cosmic blind spot. The Milky Way is a spiral galaxy. Picture a dinner plate with a bulge in the middle. We live in that flat disk, about 30,000 light years from the galactic core. When we look up or down perpendicular to this disk, we have a clear view. Billions of galaxies stretch out in those directions, visible, measurable, mapped. But when we look horizontally, parallel to the disk itself, everything changes. We're not looking out into space anymore. We're looking through our own galaxy, through billions of stars, through clouds of dust and gas that span thousands of light years, through material so dense it swallows light completely. And here's where it gets worse. The most important gravitational feature in our cosmic neighborhood, a structure so massive, it's literally pulling millions of billions of solar masses worth of galaxies toward it, sits directly behind the thickest dust laying in our galaxy. Scientists couldn't have positioned it more inconveniently if they tried. This is the zone of avoidance. And for over a century, it kept one of the universe's greatest secrets hidden from us. Dust doesn't just dim light, it erases it. Imagine trying to see a candle through a thick blanket. You're not seeing a dim flame, you're seeing nothing. Galactic dust does exactly that to distant light, visible light. The kind our eyes and optical telescopes detect can barely penetrate a few hundred light years through the galactic plane. The Great Attractor sits 250 million light years away, on the far side of that cosmic curtain. Back in the early 20th century, Edwin Hubble noticed something strange. As he mapped galaxies across the entire sky, he found them everywhere, except along one band, the galactic plane itself. Not because galaxies avoided that region, because we couldn't see them. He named it the zone of avoidance, and the name stuck. For decades, astronomers simply accepted it. They worked around it. They mapped the universe everywhere else and learned to live with this cosmic blind spot. But you can't just ignore the Great Attractor. It's pulling on everything around it, influencing galaxies across hundreds of millions of light years. To understand the large-scale structure of the universe, to grasp how matter is actually distributed in space, scientists needed to see through that curtain. They needed to pierce the veil. The problem, visible light couldn't do it. But then, they remembered something about how light works. Dust doesn't treat all wavelengths equally. It absorbs short wavelengths, blue and ultraviolet light, far more effectively than long wavelengths. This is why sunsets are red. Earth's atmosphere scatters blue light away, letting red light pass through. The same physics applies across the cosmos. Infrared light, wavelengths too long for our eyes to see, can partially penetrate galactic dust, not completely, but enough to peek through. And radio waves? Even longer wavelengths. They pass through cosmic dust almost as if it isn't there. They reveal an entirely different universe. A universe where the zone of avoidance becomes transparent. Starting in the 1990s, astronomers pointed radio telescopes at the forbidden zone, and what they found would rewrite the cosmic map. Thousands of galaxies emerged from the darkness. Not distant ones, not dim ones. Massive galaxy clusters sitting relatively close to us, hidden behind the curtain the entire time. Some were closer than well-known structures in other parts of the sky. We had been living next to cosmic giants. Giants we never knew existed. Radio telescopes detect emissions from neutral hydrogen gas, the most abundant element in the universe. And where there's hydrogen, there are galaxies. For the first time, humanity could see what had been invisible for over a century. The universe revealed a completely different face. The hidden universe, revealed somewhere out there, beyond the veil of cosmic dust, an invisible force has been pulling on our galaxy for billions of years. We didn't know what it was. We just knew something massive was tugging at us, dragging the Milky Way through space at nearly 1,000,000 miles per hour toward a region we couldn't see. Then astronomers discovered a trick. Every galaxy in the universe is surrounded by vast clouds of neutral hydrogen gas. This gas glows. It radiates at a specific frequency, a radio signal that dust cannot block, while visible light gets swallowed by cosmic fog. These radio waves pass right through, carrying secrets from the hidden universe. Astronomers tuned their receivers to listen. They called it HI mapping, named after the spectral line of neutral hydrogen. This technique promised to reveal what darkness had concealed. In 1996, a team at the Parkes Observatory in Australia aimed their telescope at the zone of avoidance, that forbidden strip of sky where the Milky Way's disk blocks our view of everything beyond. Night after night, the telescope swept across the heavens, collecting whispers from the void. What emerged was staggering. Structure after structure materialized in the darkness. Galaxy clusters containing hundreds of members, filaments of galaxies stretching across tens of millions of light years. Superclusters rivaling anything in the observable universe. But one discovery demanded attention. Exactly where astronomers predicted the Great Attractor would be, they found it. The Norma Cluster. Sitting 220 million light-years away, thousands of galaxies crammed into a relatively small volume of space, each galaxy containing hundreds of billions of stars, all bound together by gravity into a single, colossal structure. The numbers confirmed what they suspected. By measuring how fast galaxies moved within the cluster, astronomers calculated its mass. The numbers matched predictions. The Norma Cluster was indeed pulling on the Milky Way. But here's where it got interesting. It wasn't enough. The gravitational tug felt across hundreds of millions of light years required something more massive than even this enormous cluster. The Norma Cluster was the heavyweight champion of the region, but it wasn't fighting alone. It was part of something vastly larger. Multiple clusters and superclusters working in concert, their gravity combining to create the force that had been pulling on us all along. And there was more. Running through the zone of avoidance was something else entirely. A massive filament of galaxies spanning over 100 million light years. Astronomers called it the Great Attractor Wall, sometimes the Norma Wall. Imagine a cosmic highway, billions of light years long, connecting different regions of the universe. The Norma Wall was one of these highways, and it contained multiple galaxy clusters, each as impressive as the Norma cluster itself. Picture discovering an entire mountain range hidden behind fog. As the fog clears, you don't see one peak. You see dozens. Mountains connected by ridges and valleys, forming a system far more complex and far more massive than any single structure. That's what the Great Attractor was. Not one thing. A region. A concentration of structures. A node where cosmic filaments intersected, where the universe itself seemed to fold inward under the weight of collapsed matter. But the radio surveys revealed something even more profound. The galaxy density in the zone of avoidance matched the density everywhere else. The region wasn't special. It wasn't unique. The dust that had hidden it for so long wasn't concealing anything exotic or strange. Behind the curtain was the same universe we already knew. The same types of galaxy clusters. The same cosmic web. The same structure repeated across billions of light years. Except for one crucial detail. The structures hidden in the zone of avoidance were positioned perfectly, precisely where they needed to be to explain every observation astronomers had made. The cosmic flow pulling thousands of galaxies across millions of light years suddenly made sense. The Norma cluster and its companions weren't random collections of stars and gas. They were the gravitational engine driving the universe's motion around us. But as these discoveries solved one mystery, they opened another. If the Great Attractor was this massive, this influential, what else was hiding in the regions we still cannot see? The Parkes telescope had pierced one veil, but the universe contains many more. By the early 2000s, the hunt intensified. Observatories around the world and above it joined forces, each wielding a different weapon in their arsenal. They didn't just see what was hidden behind the cosmic dust. They built a three-dimensional map of the forbidden zone, revealing not just structures, but how those structures wove into the larger cosmic web. Then came X-rays. Here's the thing about X-rays. They're violent. They're radiation with such punishing energy that they can smash through dust that would completely block visible light. You'd think the opposite would be true, that shorter wavelengths would be stopped more easily, but X-rays don't care about your intuition. They punch through. Space-based telescopes like Chandra and XMM Newton scanned the zone of avoidance, hunting for the telltale glow of superheated gas trapped between galaxies. And they found it. The Norma cluster blazed in X-rays, its gas screaming at temperatures of tens of millions of degrees, heated by the fury of countless stars and supernovae burning across cosmic time. That glowing gas became a cosmic scale. The X-ray brightness revealed the cluster's mass with precision that earlier methods could never achieve. Combine that with infrared observations and radio data, and suddenly astronomers could calculate the total mass of the Great Attractor region. They could pin down the number. And when they did, they got a shock. Earlier estimates had suggested the Great Attractor might contain the mass of 100,000 galaxies. The new measurements said those estimates were too high, not a little bit, by a factor of 10. The actual mass was only about 10,000 galaxies worth. Still enormous, still capable of pulling galaxies across millions of light years, but not nearly what anyone expected. This created a crisis in the numbers. If the Great Attractor wasn't massive enough to explain what astronomers were seeing, what was it that was pulling so hard on galaxies even farther out. The velocities didn't match. The gravitational pull required more mass than the Norma region contained. Something was missing from the equation. The answer came from looking deeper. Astronomers pushed their telescopes farther into space, past the zone of avoidance, into regions where the cosmic dust couldn't hide them anymore. They mapped galaxy positions and motions across vast distances, and what they discovered rewrote the story entirely. 650 million light-years away, beyond the Great Attractor, beyond the zone of avoidance, beyond everything astronomers had been studying, sat a structure so massive it made everything else look small. The Shapley supercluster. Harlow Shapley had discovered it decades earlier, but now astronomers finally understood what it meant. It contained tens of thousands of galaxies, far more than the Norma region, and it was pulling. The Milky Way wasn't just falling toward the Great Attractor, it was falling toward Shapley beyond it. The Great Attractor wasn't the destination, it was a stepping stone on a much longer journey. Picture this. You're rolling a ball down a hill, you see the valley directly ahead, and think that's where it's going. But the valley itself sits on the slope of an even bigger mountain. The Great Attractor was the valley. Shapley was the mountain. This changed everything. The peculiar velocities of galaxies in our region weren't caused by local structures alone. They were caused by gravitational influences stretching across nearly 1 billion light-years of space. The cosmic flow patterns astronomers had been mapping weren't a complete picture. They were just one brushstroke in a painting far grander than anyone had imagined. Radio telescopes, X-ray observatories, and infrared surveys had finally pierced the zone of avoidance. They had revealed what lay hidden in the darkness. But in solving one mystery, they had uncovered something far bigger. The Great Attractor wasn't the answer. It was just the beginning. It was the moment astronomers realized how small their understanding really was. And that bigger picture, the one they thought they'd finally grasped, kept getting bigger. The Norma Cluster, a window into the invisible universe. Imagine light traveling through space for 220 million years. It left its source when the first flowers bloomed on Earth. When it finally reaches our telescopes today, it carries a message from the Triassic period, a time before dinosaurs ruled the world. And what that ancient light reveals is staggering. When astronomers finally got a clear view of the Norma Cluster, they weren't just looking at a loose collection of galaxies floating in space. They were looking at a monster, a dense, violent, dynamically chaotic structure containing thousands of galaxies, each one screaming through space at speeds exceeding 1,000 miles per second. These aren't random trajectories. Each galaxy is locked in an orbital dance, pulled relentlessly toward the cluster's center by the combined gravitational weight of everything around it. Some of these galaxies are diving into the core for the first time, accelerating as they plunge deeper into the gravitational abyss. Others are seasoned veterans. They've completed orbit after orbit over billions of years, their paths carved and reshaped by countless close encounters with neighboring galaxies. It's like watching a swarm of bees circling a hive. Each individual bee moves in what looks like chaos, but the swarm maintains structure, organization, and purpose. Except here, each bee is a galaxy containing hundreds of billions of stars, and the entire swarm spans millions of light years. At the cluster's heart sit the true tyrants, elliptical galaxies so massive They've grown to hundreds of times the size of our own Milky Way. These aren't spiral galaxies like ours. They're shaped like footballs, like spheres, like cosmic predators. And that's exactly what they are. Every time a smaller galaxy wanders too close, tidal forces rip it apart like tissue paper. The stars get absorbed. The galaxy gets consumed. The monster grows larger. Billions of years of feeding has transformed these central giants into gravitational leviathans. Each one a cosmic heavyweight that dominates everything nearby. But between the galaxies exists something even stranger: hot gas. Incredibly, impossibly thin by Earth standards. It counts as a near-perfect vacuum. Yet it's so vast, so expansive, that it contains more mass than all the visible stars in every single galaxy in the cluster combined. This gas burns at 50 million degrees Fahrenheit, hot enough to strip electrons from atoms and flood space with X-rays. When we look at the cluster through X-ray telescopes, it glows like a cosmic furnace, revealing the gravitational architecture in stunning, terrible detail. Yet even this invisible ocean of superheated gas, this mass that dwarfs all the stars we can see, isn't the dominant force here. There's something else. Something far more massive, something that generates more gravitational pull than all the galaxies and all the hot gas combined. We call it dark matter. This is the cosmic elephant in the room. We cannot see it. It doesn't emit light. It doesn't absorb light. It doesn't interact with anything, except through gravity. We know it exists for one reason, and one reason alone. The math doesn't work without it. The galaxies in the Norma cluster are moving too fast. They're orbiting with too much velocity. By all calculations, they should have torn the cluster apart billions of years ago. The cluster should have exploded into the void, its members scattered across the universe. But it didn't. Something invisible is holding it together. Something we cannot directly observe is providing the extra gravitational glue that binds these galaxies in their cosmic embrace. The numbers are staggering. Dark matter comprises roughly 85% of the Norma cluster's total mass. Everything we can see, every galaxy, every star, every atom of hot gas, all the normal matter combined, accounts for just 15%. The cluster is mostly invisible, mostly unknown, mostly made of something science cannot touch, cannot measure, cannot directly observe. Yet it dominates. It shapes how galaxies move. It determines the structure's long-term fate. It is the universe's hidden architect. The Norma cluster isn't just a collection of galaxies. It's the largest concentration of mass in an entire region of space called the Great Attractor. It doesn't exist in isolation. It's a gravitational anchor point, a cosmic landmark, in a universe far more complex than we ever imagined. And what it reveals, what it demands we confront, is this: most of reality is hidden from us. Most of the universe is made of something we don't understand, something we can only infer from its gravitational effects. We are living in ignorance of the very substrate that holds our cosmos together. Bunch, the Great Attractor, there's something out there pulling on us. Right now, at this very moment, the Milky Way is being dragged through space by a force so powerful, so relentless, that galaxies across an entire region of the universe are surrendering to it. And for decades, we didn't even know why. Beyond what we could see, hidden behind a cosmic veil called the zone of avoidance, lies a structure so massive that it warps the fabric of reality itself. Superclusters surround it. Not just one, many, each containing hundreds, sometimes thousands of galaxies. And together, they form something even bigger, the Norma region, a gravitational architecture that spans 100 million light years. This is the thing that's been pulling on us all along, but let's actually grasp the scale here. Try to picture 10,000 galaxies. Each one holds roughly 100 billion stars. Each star is absolutely enormous compared to planets, yet pathetically tiny against the vast gulfs of space between them. Now compress all of that, 10,000 galaxies, each with 100 billion suns, into a region just a few hundred million light years across. What do you get? A gravity well so deep, so powerful, that it warps space itself. Imagine space as a rubber sheet, stretched perfectly flat. Now place a bowling ball on it. The sheet curves down, it sags. That depression, that's a gravity well. But that's only 2 dimensions. In reality, gravity wells exist in all 3 dimensions simultaneously, warping space inward from every direction at once. The Norma region creates one of the deepest gravity wells in our corner of the universe, and everything nearby is falling into it. Any galaxy close enough begins sliding down those cosmic slopes, accelerating as it plunges deeper. The Milky Way? We're perched on the outer edge of this well. We're falling too. Just slowly, more slowly than the galaxies already spiraling toward the center. Think of a marble rolling across a tabletop. When it reaches the rim of a bowl, it doesn't instantly plummet to the bottom. Instead, it circles the edge, gradually spiraling inward, pulled by the invisible slopes beneath it. That's us. We're on the rim, circling slowly, while deeper regions pull with ever-increasing strength. But here's what makes this gravity well truly strange. It's not symmetrical. In a perfect, orderly gravity well, matter pulls equally from all directions toward one central point. The Great Attractor's well is twisted. It's elongated along some axes, compressed along others. The geometry is warped and uneven, and that asymmetry tells us something crucial. This isn't one single massive object. It's multiple clusters, each one contributing its own gravitational distortion, each one adding its own pull to the overall field. The result? A gravity well with ridges and valleys, fast lanes and slow lanes, regions where gravity pulls harder, regions where it pulls softer. Galaxies don't fall straight down into this well. They follow curved, spiraling paths, moving inward while also drifting sideways, tracing out complex 3-dimensional trajectories through space. Some approach from one direction, others from another. The paths interweave like threads being woven into fabric. Over billions of years, these galaxies will all converge. They'll reach the bottom of the well, where the densest concentrations of matter already wait. We can actually see this happening. Not directly. We can't watch billions of years unfold, but we can see the fingerprints gravity leaves behind. Light from distant galaxies travels across space toward us, but when that light passes through the Great Attractor region, it encounters some of the most massive structures in the universe, and gravity bends it. This isn't theoretical. Einstein predicted it over a century ago, and we've confirmed it countless times since. Massive objects warp space around them like a bowling ball. Curves space-time. Everything nearby bends around them. It's called gravitational lensing. Imagine looking through an old, imperfect window. the kind with waves and irregularities in the glass. Objects on the other side appear distorted, stretched, sometimes even multiplied. Gravitational lensing works the same way, except the window isn't glass. It's space itself, warped by incomprehensible amounts of mass. The stronger the gravitational field, the more dramatic the distortion. And the Great Attractor's field is powerful enough that modern telescopes can see these distortions. Background galaxies stretched into arcs, sometimes split into multiple images of themselves. Astronomers use these cosmic mirages to map the distribution of mass throughout the region, including the dark matter we can't see directly, but know is there. These lensing effects confirm what the numbers suggest. The Great Attractor region contains a concentration of mass so extraordinary, it reshapes the universe around it. But mass alone doesn't tell the whole story, because the Great Attractor isn't finished. It's not static. It's still evolving, still pulling, still reshaping the cosmic structure around it. And we're caught in its grip. Imagine a cosmic river, not a river of water, but a river of galaxies. Thousands upon thousands of them, all flowing inexorably toward a single point. This river is alive. It's constantly changing. Galaxies collide and merge, adding their mass to the flow. Billions of years ago, this current was weaker, less organized. Billions of years from now, it will swell even more as fresh galaxies join the procession. The universe is expanding, driven by an invisible force called dark energy, pulling everything apart. But here, in this region, gravity has staged a rebellion. Gravity wins. These galaxies aren't drifting apart with the cosmos. They're falling together, locked in a battle against the universe's own expansion. And gravity is winning, at least for now. Yet even this colossal concentration of tens of thousands of galaxies, this structure that dominates our cosmic neighborhood, is merely a fragment of something so vast, it breaks our ability to conceive of scale. For most of human history, we thought Earth was the center of everything. Then we learned Earth orbits the sun. Then we learned our sun is one of billions in our galaxy. Then we learned our galaxy is one of billions in the observable universe. Each revelation pushed us farther from the center, made us smaller, made us less significant. And in 2014, astronomers added another crushing line to our cosmic address. They discovered we live inside a structure so immense, so incomprehensibly vast, it forced us to rewrite the cosmic hierarchy. They called it Laniakea. In Hawaiian, it means immeasurable heaven. The name is perfect. Laniakea is a supercluster, a gravitational basin containing roughly 100,000 large galaxies and an uncountable multitude of smaller ones. It stretches 500 million light years from edge to edge. Think about that. Light, the fastest thing in the universe. It takes light 500 million years to cross it. When the photons currently arriving from Laniakea's far edge first began their journey, the first creatures with spines were just crawling out of Earth's oceans. Astronomers discovered Laniakea the same way they found the Great Attractor, by mapping cosmic flow, by tracking the velocities of thousands of galaxies and plotting where they're heading. The data revealed streamlines, invisible channels showing how matter moves through space. And those streamlines revealed boundaries, edges where galaxies flowing in one direction stop, and galaxies flowing in another direction begin. Think of it like watersheds on Earth. Water on one side of a mountain ridge flows to one ocean. Water on the other side flows to another ocean. Cosmic watersheds work the same way. They divide galaxies, flowing toward different gravitational basins. Laniakea is one such basin. And within its boundaries, every single galaxy, all 100,000 of them, is flowing toward the same gravitational heart, the Great Attractor. The Milky Way is trapped in this flow. So is Andromeda. So is the entire local group, the Virgo cluster, the Hydro-Centaurus supercluster. Hundreds of thousands of galaxies spread across 500 million light-years of space. All of them, all of us, sharing one common destiny. Picture a cosmic valley. Mountains rise on all sides. Raindrops fall on those mountains. They run downhill. They merge into streams. Streams become rivers. And all those rivers converge at the valley floor, at the lowest point. That lowest point is the Great Attractor. It's not a physical object you could visit. It's not a place with coordinates you could punch into a spaceship. It's a gravitational center, an invisible sink toward which everything falls. And we're falling too. Right now. Silently, inevitably, pulled by the weight of 100,000 galaxies toward a horizon we can never see. The universe's grand architecture. Imagine stacking 100,000 galaxies together. Each one contains hundreds of billions of stars. Now add all the dark matter, that invisible glue holding everything in place. The total mass? About 100 quadrillion times heavier than our sun. Written out, 100,000 trillion stellar masses. The number is so absurdly large that your brain simply gives up trying to comprehend it. It's like asking someone to feel the difference between $1 billion and $1 trillion. Sure, mathematically one is bigger. But your intuition, it breaks down completely. This is Laniakea, our cosmic supercluster. The structure we now know contains us. But here's where it gets strange. Despite all that mass, Laniakea is not held together by gravity. Let that sink in. 100 quadrillion stellar masses, and gravity cannot bind them. This seems impossible until you understand one devastating fact. The universe is expanding. And at these scales, that expansion is stronger than gravity itself. Galaxy clusters bound together. Our local group bound together. But Laniakea, the sheer distances are so vast that space itself is tearing it apart. Right now, galaxies at the edges are being pulled away. The universe is literally dismantling this supercluster in real time. Only the central region, the Great Attractor, will remain gravitationally bound as billions of years pass. Everything else will eventually drift into the cosmic void. This raises an unsettling realization. We don't live in a stable universe. We live in a collapsing one. Our address tells the story. Earth, Solar System, Milky Way Galaxy, Local Group, Virgo Cluster, Virgo Supercluster, Laniakea, 7 nested structures, 7 levels of organization, each incomprehensibly larger than the one before. And we're not simply orbiting our star. We're falling through all of them simultaneously. Different structures pull us in different directions. Each one contributes to our motion through space. It's like being caught in 7 currents at once, each flowing a different way. The Great Attractor, that mysterious gravitational anomaly, pulling thousands of galaxies toward it isn't some isolated cosmic accident. It's the gravitational anchor organizing the entire supercluster. It's the reason our galaxies move the way they do. 500 million light-years of motion, all orchestrated by one dominant gravitational point. But mapping Laniakea created a new problem, one that still troubles astronomers today. Where exactly does Laniakea end, and where do other structures begin? Imagine standing in the middle of the ocean. You can feel the water. You can measure the currents. You can track the waves, but seeing the ocean's full extent, where it meets the continents, how deep it goes, where the currents truly originate, that requires a perspective you simply don't have. You're trapped inside it. We face the same problem. We're embedded in Laniakea. We're trapped inside the very structure we're trying to map. How do you measure something when you're standing inside it looking out? The breakthrough came from precision. Astronomers stopped relying on a single measurement: redshift. Redshift tells you how fast a galaxy is moving away from us, but it's contaminated. It mixes cosmic expansion with local gravity into one blurry number. The new approach was elegant. Separate them. Measure how fast a galaxy recedes due to the universe's expansion alone. Then measure how fast it's moving due to local gravity pulling it around. With both numbers, you can reconstruct the gravitational field itself, the invisible architecture holding everything in place. Think of mapping wind patterns on Earth. You don't just measure speed, you measure direction. You measure what's causing the motion. Apply that same logic to the cosmos, and suddenly the structure reveals itself. What emerged was breathtaking. Laniakea isn't a blob. It's not a random scattering of galaxies. It's a web, a three-dimensional spiderweb made of pure gravity. Dense filaments of galaxies crisscross through space, intersecting at massive nodes. Cosmic junctions where tens of thousands of galaxies cluster together. The Great Attractor region forms the largest node, but others dot the supercluster. The Virgo cluster alone contains over 1,000 galaxies and sits just 60 million light-years away from us. The Hydra Centaurus supercluster forms another massive junction farther out. The Norma cluster marks the absolute center, the heart of the Great Attractor itself. These aren't separate islands. They're connected by cosmic bridges, highways of galaxies flowing along gravitational currents. Matter streams along these filaments like water through channels. Between the filaments lie vast voids, empty spaces, regions containing almost no galaxies at all. In these voids, gravity pulls outward instead of inward. They're the negative space of the cosmic web, the gaps that give the structure its form. The entire supercluster is a living, breathing network, a grand cosmic architecture more complex than any city, more intricate than any forest. And we live inside it, moving along its currents, pulled by its gravity, falling deeper into its structure with every passing moment. This is not just where we live. This is what we live inside. And we're only now learning to see it. Imagine rivers carved into the fabric of space itself. In these cosmic channels, galaxies don't just drift. They race. They plummet. They're pulled by invisible hands at speeds far greater than galaxies, drifting in the empty voids between them. This makes sense because the filaments, these narrow threads connecting galaxies, they're crowded, dense, heavy. More mass means stronger gravity. Stronger gravity means faster pull. Think of water flowing downhill. The main channel moves fastest. But in the quiet pools and eddies, water barely moves at all. Laniakea's filaments are those main channels, and galaxies are being dragged toward the Great Attractor at speeds that would make your head spin. The voids. They're the still pools. Galaxies there drift slowly, or they escape entirely, tugged away by gravitational forces that exist beyond Laniakea's borders. But here's where it gets mind-bending. Laniakea contains roughly 500 galaxy groups and clusters. Some are small, just a dozen large galaxies huddled together. Others are titans. The Virgo cluster alone harbors more than 1,000 galaxies we can actually see. Probably many more are hiding just beyond our reach, too faint to detect. The Fornax cluster is another heavyweight, packed with hundreds of massive galaxies. Each cluster pulls on its neighbors. Each one participates in a cosmic dance that has been choreographed for billions of years. Now, there's something invisible in all this, something that dominates absolutely. For every kilogram of normal matter, every star, every planet, every atom you can touch, roughly 6 kilograms of dark matter are lurking in the same space, unseen, undetectable by light. Dark matter is the gravitational skeleton. It's the scaffolding on which everything else accumulates. Without it, galaxies wouldn't cluster. Clusters wouldn't merge into superclusters. The entire large-scale structure of the universe would look completely different. We know dark matter is real. We can see its fingerprints everywhere. In how fast galaxies spin, in the way light bends around massive objects, even in the ancient light of the cosmic microwave background. The evidence is overwhelming. But here's what makes astronomers lose sleep at night. Laniakea is staggeringly massive. 100,000 galaxies, 500 million light-years across. It's one of the largest structures we've ever found, and yet, and this is the part that troubles us, galaxies at its edges are moving in ways we can't fully explain. They're being pulled by something beyond Laniakea, something bigger, something that makes even this immeasurable cathedral of galaxies look small. If you trace the motion of a single galaxy backward through time, you'll follow a path that winds through space like a river flowing to the sea. It curves around dense regions. It dances past other galaxies. Eventually, it leads to the Great Attractor. Now imagine doing this for 100,000 galaxies. Layer those paths on top of each other. What you get is a three-dimensional web of trajectories, so intricate, so beautiful, it looks more like art than astronomy. But make no mistake, these aren't artistic fantasies. These are real paths, calculated from real velocities, measured from real observations. Every line represents an actual journey through space, a galaxy falling through the gravitational field like a drop of water following a river to the sea. Where these streamlines converge, matter piles up. Where they spread apart, voids open up. The pattern tells a story, not just where galaxies are today, but where they came from and where they're going. And some streamlines? They stretch beyond Laniakea's boundaries. These represent the exiles, galaxies on the edge, caught between two worlds, uncertain whether they'll remain part of the supercluster or whether they'll be torn away by competing forces. Like a river delta splitting into branches before it reaches the ocean, the cosmic current divides. Some galaxies flow one direction, others flow another way, and the boundary between them keep shifting, always changing, caught in an eternal struggle between gravity's competing masters. Imagine standing at the edge of a cosmic whirlpool. You're not in it yet, but you feel it. That tug, that inexorable pull, drawing you toward the center. For the galaxies clustered around Laniakia's boundaries, this is their reality. They're caught in a gravitational tug-of-war, yanked between our supercluster and the massive structures surrounding us. But we're not passive observers in this drama. We're actors in it. The Milky Way is moving. We can trace our trajectory with stunning precision. Right now, we're hurtling toward the Great Attractor at 600,000 miles per hour. But that's only half the story. We're also sliding sideways, caught in a cosmic current that pulls us in multiple directions at once. Our path isn't a straight line. It's a long, slow spiral, circling inward, descending deeper into the gravitational well like water circling a drain. 10 billion years from now, if nothing changes, we might finally reach the densest regions of the Great Attractor. But something will change. Something always does. And we're not alone on this journey. Andromeda, our nearest galactic neighbor, follows a streamline parallel to ours, flowing toward the same cosmic furnace. In 4 billion years, Andromeda will collide with us. Two great spiral galaxies, each containing hundreds of billions of stars, will smash together in a collision that will reshape both forever. The result won't be chaos. It will be a larger, older elliptical galaxy, born from the violent merger of two titans. But even this new galaxy, this amalgamated monster, will continue falling. The same gravitational current that drew in both ancestors will still have its hooks in them. Look outward, and the picture becomes staggering. The Virgo cluster, an assemblage of thousands of galaxies, plunges toward the Great Attractor at speeds exceeding 1 million miles per hour. Dozens of other clusters follow their own paths, each a river of galaxies converging on a central basin. Over billions of years, these streams will keep flowing inward. Some clusters will merge with the existing structures at the center, adding their mass to the growing behemoth. Others will overshoot, pass through the dense heart, and swing back out, like pendulums caught in the universe's most massive gravitational swing. But this infall comes at a price. When galaxies plunge into these dense regions, gravity tears them apart. The tidal forces are so fierce that stars get ripped away from their galaxies, leaving long trails of stellar debris stretching across space like cosmic blood in the water. Gas clouds collide and compress. The collision ignites a fury of star formation, brilliant, brief, and doomed. But this burst of creation doesn't last. The act of falling transforms galaxies. It changes them fundamentally, irreversibly. Look at the galaxies already residing in the Great Attractor region, and you see the evidence. They're older. They're redder. They contain fewer young stars than their counterparts in less crowded neighborhoods. Why? Because their gas was stripped away during the violent infall. Star formation shut down. The galaxies became dead, frozen in time, their days of creation behind them. The streamlines tell another story too, a history of Laniakea itself. When astronomers reverse time, running the simulation backward, they see a younger supercluster, less concentrated, more spread out. The galaxies at the edges hadn't yet felt the full weight of the Great Attractor's pull. Laniakea was still forming, still organizing itself from the quantum fluctuations born in the first fractions of a second after the Big Bang. A supercluster still in the process of becoming. But look forward into the deep future. If gravity were the only force at play, the story would be one of eventual collapse. All these streams converging, all this matter falling inward. The individual galaxy clusters would merge. The filaments connecting them would condense. Laniakea would collapse into a single, incomprehensibly massive structure, the largest galaxy cluster imaginable, containing the combined light and mass of hundreds of thousands of galaxies. Everything moving toward the center would finally arrive. The cosmic infall would complete. Except that won't happen. There is another player in this story, a force we barely understand. Dark energy. It doesn't push or pull in any conventional sense. It's woven into the fabric of reality itself, a mysterious component of the universe that grows stronger as space expands. And it's winning. As the universe ages, dark energy gains ground on gravity. It accelerates the expansion of space itself. Eventually, this force will overcome gravity, even at the scale of entire superclusters. The streamlines we map today, showing galaxies flowing toward the center, will reverse. Everything will start moving outward instead. The cosmic expansion will tear Laniakea apart, stretching the supercluster until the very concept of a unified structure becomes meaningless. For now, though, the rivers still flow inward. 100,000 galaxies, all falling together, all bound by gravity and shaped by the initial conditions set 13.8 billion years ago, when time itself began. Each galaxy following its predetermined path through the cosmic ocean. But even this vast and terrible current is not the end. Beyond Laniakea's boundaries, even mightier currents surge. The universe is pulling on us from all directions, at speeds that dwarf even our plunge toward the Great Attractor, 1,300,000 miles per hour. The cosmos is vast, and we are falling through it, spiraling toward a future that dark energy will ultimately rewrite. Our entire galaxy is plummeting through space at over 1 million miles per hour toward something massive, something we call the Great Attractor. Let that sink in for a moment. A spacecraft traveling at that speed could reach the moon in just 11 minutes. Mars? 3 hours. Neptune, lurking at the edge of our solar system, about 4 days. We're moving faster than anything humanity has ever built. Faster than anything we've ever dreamed of building. But here's the twist that breaks your intuition. You don't feel it. Not one bit. You don't feel Earth orbiting the sun. You don't feel the sun orbiting the galaxy. You don't feel the galaxy hurtling through the cosmos. Nothing. Because everything moves together. You, Earth, the entire solar system. We're all passengers on the same ship, traveling at the same velocity. There's no wall sliding past your window, no stationary point to measure against. It's only when you look outward to other galaxies and watch their light shift that the motion becomes visible at all. But here's where it gets really weird. The speed doesn't have a single answer. It depends on what you're measuring against. Compared to the cosmic microwave background, the ancient radiation left over from the Big Bang itself, the Milky Way moves at 800,000 miles per hour. Compare us to the center of our local group of galaxies, and we're going 300,000 miles per hour. Measure us against the Great Attractor, and suddenly we're screaming through space at 1.3 million miles per hour. All three numbers are correct, simultaneously. All true. Think of it this way. You're sitting in a car on the highway. Relative to the car, you're perfectly still. Relative to the road, you're moving at 60 miles per hour. Relative to another car passing you at 70 miles per hour, you're actually moving backward at 10 miles per hour. All three statements are true at the same time. Now scale that up. Instead of a highway, imagine galaxies falling through curved space. Instead of miles per hour, imagine millions. That's the cosmos. And the motion gets more complicated still. Andromeda, our neighboring galaxy, is rushing toward us at 250,000 miles per hour. But that's not part of the Great Attractor's pull. Andromeda and the Milky Way are locked together by gravity, bound in a slow, cosmic collision that will take billions of years to unfold. They're falling toward each other while simultaneously falling toward the Great Attractor. Motion within motion, layer upon layer. The Virgo cluster is diving toward the Great Attractor even faster than we are. It's deeper in the gravitational well, where the pull is stronger. And here's something beautiful. Galaxies on the near side of Virgo move at slightly different speeds than those on the far side. That tiny difference in velocity tells us something profound. It reveals the strength and direction of the gravitational field, like watching water accelerate as it flows downhill. The closer you are to the source, the faster you fall. We know all this is real because we've measured it multiple ways. Astronomers watch light from distant galaxies stretch and compress. Redshift for objects receding, blue shift for objects approaching. They calculate distances using independent methods. They map the three-dimensional motion of galaxies through space. Every measurement agrees. Every technique confirms it. The Milky Way is falling toward the Great Attractor, and nothing can stop it. Well, almost nothing. Dark energy can. In fact, dark energy will. The universe is accelerating. This mysterious force, dark energy, is driving the expansion of space itself, and it's getting stronger. One day, this expansion will become so powerful that it overwhelms the gravitational pull of the Great Attractor. When that happens, Laniakea, the supercluster that contains us, will begin to tear itself apart. Galaxies at the edges will be ripped away first, then those closer to the center. The Great Attractor won't pull forever. The universe will pull harder, and in the end, everything will drift alone into the dark. Billions of years from now, the very atoms holding galaxies together will feel gravity's relentless grip. But that's the distant future. Right now, in this moment, gravity rules everything. Right now, we're all falling. But this fall tells us something profound. It reveals the mass of what's pulling us. Newton gave us the equation: force equals mass times distance. So here's the trick astronomers use. They watch how fast galaxies move at different distances from the Great Attractor. The faster they move, the more mass must be there. The math is simple. The answer is staggering. The Great Attractor contains tens of thousands of galaxies worth of mass. Most of it dark matter, invisible to our telescopes, detectable only through its gravitational reach. But then something strange happened. The numbers stopped working. Galaxies far from the Great Attractor were moving too fast. Far too fast. Their velocities suggested they were being pulled by something even more massive, something hiding beyond the Great Attractor entirely. By the early 2000s, astronomers thought they'd solved this mystery. They'd mapped the Norma cluster. They'd discovered Laniakea. They'd traced the cosmic currents, showing how galaxies flowed through space like water down a drain. The picture was complete. The Great Attractor was the gravitational center of our supercluster, pulling everything with the combined weight of multiple galaxy clusters hidden behind a cosmic blind spot called the zone of avoidance. Case closed, except the observations kept screaming that something was wrong. Galaxies on the far side of Laniakea, the side facing away from the Great Attractor, were moving faster than they should. Much faster. Their velocities told a story the theory couldn't explain. Something beyond Laniakea was pulling on them. Not gently, powerfully. A gravitational force stronger than anything the Great Attractor could generate. So scientists did what scientists do. They checked their measurements. They recalculated every distance. They verified every velocity using completely independent methods. The anomaly didn't disappear. It only grew louder. Then came the surveys that changed everything. The Cosmic Flows Project kept expanding, adding more galaxies to their cosmic map, pushing deeper and deeper into the universe's structure. By 2005, they'd mapped galaxy motions out to 650 million light-years away, far beyond where anyone thought structure ended, far beyond Laniakea's boundaries. And the data revealed something that shouldn't exist. The Great Attractor itself was moving, not drifting with cosmic expansion, not staying put, moving with its own peculiar velocity, pulled by something else, something farther away, something more massive. Let that sink in. The structure that pulls on 100,000 galaxies, the gravitational center of our entire supercluster, the mass equivalent of tens of thousands of galaxies combined. It was being pulled like a leaf in a current by something even larger. It was like discovering that the vast ocean you've always known is actually just a bay. And beyond the horizon lies a larger ocean you never knew existed. This larger force had a name: the Shapley Supercluster. Harlow Shapley discovered it back in the 1930s, and it remains the most massive concentration of galaxies we can observe nearby. It lurks 650 million light-years away, beyond Laniakea, beyond the Great Attractor, in regions where observing becomes difficult, but never impossible. Shapley contains tens of thousands of galaxies, far more than the Great Attractor region. Its gravity stretches across nearly 1 billion light-years of space, and everything nearby, including the Great Attractor, bends toward it. Then in 2005, X-ray surveys measured the Great Attractor's mass with unprecedented precision. The results shocked everyone. The Great Attractor contained only about 1/10 the mass that previous estimates suggested. Instead of 100,000 galaxies, it held roughly 10,000. Still enormous. Still the dominant structure in Laniakea, but nowhere near massive enough to explain the motions astronomers observed. The crisis was real. Cosmology had a problem on its hands, and no one knew where the answer lay. Here's what we thought we knew. The Great Attractor was pulling our galaxy through space. It had to be. The numbers didn't lie. Galaxies around us were moving too fast to be explained by anything closer. But then a troubling question emerged. Was the Great Attractor actually massive enough to do what we were seeing? The math didn't quite add up, and that's when astronomers had to look further, beyond the Great Attractor, beyond everything we thought we understood about our cosmic neighborhood. They found their answer in the Shapley region, but accepting it meant accepting something deeply unsettling. Everything we believed about the large-scale structure of the universe was incomplete. Our maps were wrong. Laniakea wasn't some isolated supercluster sitting alone in the cosmic dark. It was just a piece of something far, far larger. A stepping stone, and that meant redrawing every map, rethinking every theory about how gravity shapes the universe on its grandest scales. Not everyone wanted to accept this. Some astronomers pushed back hard. They argued the measurements were flawed. They suggested dark matter distributions could explain everything without invoking some hidden attractor beyond Laniakea. They proposed alternatives, cosmic voids pushing from behind instead of attractors pulling from ahead. Each theory had its appeal. Each one had fatal flaws, and the data kept coming. Survey after survey, measurement after measurement. More galaxies plotted on the map, and every single one of them pointed toward the same unavoidable conclusion. The Milky Way, Laniakea, the Great Attractor, everything in our cosmic neighborhood. We were all falling toward Shapley. Multiple independent studies confirmed it. Different methods. Same answer. The scientific consensus had to shift. What seemed like the final answer turned out to be just another chapter in a much longer story. The Great Attractor was real. Its pull was real. But it wasn't the end point. It was part of something bigger. A stepping stone on a path toward an even more colossal destination. Astronomers had been staring at one tree the entire time, completely missing the forest around them, and that forest stretched farther than anyone had dared imagine. Somewhere in its depths, something truly massive was pulling on everything within reach. Here's what makes this even more remarkable. The Shapley supercluster isn't hidden. It's not behind some zone we can't see through. It sits right there in the clear night sky, visible to anyone with a decent telescope and the knowledge of where to look. Scientists discovered it nearly 100 years ago, so why did it take until now to realize it was pulling on us? Distance. Pure, simple distance. 650 million light-years away, so impossibly far that astronomers dismissed it as irrelevant. Surely something that distant couldn't influence our local galactic neighborhood. They were wrong. Gravity doesn't work that way. Yes, it weakens with distance. Yes, it gets fainter and fainter, but it never actually stops. The math is unforgiving. Gravity extends infinitely outward. Beyond a certain range, the effect becomes too small to measure, too small to matter practically. But Shapley sits right at that threshold, right at the edge where we can still measure its whisper. Its pull on the Milky Way is faint compared to nearby sources, barely perceptible. But when you account for Shapley's staggering mass, that faint pull becomes significant. Over billions of years, it adds up to something enormous. The numbers are almost hard to comprehend. The Shapley supercluster's core contains roughly 100,000 galaxies, similar to Laniakea. But its gravitational influence doesn't stop there. When astronomers map Shapley's full reach, they discover it affects structures stretched across more than 1 billion light-years of space. One of the largest gravitational domains anywhere nearby. Imagine gravitational influence as a sphere expanding outward from a mass. The bigger the mass, the bigger the sphere. Shapley's sphere is so immense it completely encompasses Laniakea, encompasses us. We're living inside Shapley's gravitational domain without even realizing it. We're not anywhere close to its center. We're on the outskirts, in the suburbs of this cosmic giant, and we're falling toward it. Slowly, imperceptibly slowly, from a human perspective. But over billions of years, that slow fall becomes a journey across the cosmos. The evidence is written in the motions of galaxies. Those closer to Shapley move faster toward it. Those farther away move slower. But they all show the same directional bias, the same inexorable pull. We're all being drawn inward, like water spiraling toward a drain. Except the spiral takes billions of years to complete. Our cosmic neighborhood harbors a dark secret, and it's pulling us toward oblivion. The Milky Way isn't just drifting through space. It's falling. So is everything around us. The local group, the Virgo cluster, the Great Attractor itself, all of it, tumbling down a gravitational slope towards something so massive, so incomprehensibly powerful, that it commands the motion of billions of galaxies across a region of space larger than anything we thought possible. That something is Shapley. For decades, astronomers believed they'd mapped the cosmic hierarchy. Galaxies clustered into groups. Groups gathered into clusters. Clusters assembled into superclusters. The story was neat, complete, done. But it wasn't. When scientists peered deeper into the cosmic web, mapping tens of thousands of galaxies and calculating their three-dimensional velocities with unprecedented precision, the universe revealed a darker truth. Everything was moving. Not randomly, not toward multiple centers, but toward one place, toward Shapley. And the closer structures got, the faster they accelerated, pulled by gravity that intensified with every light year traversed. This discovery shattered the old definitions. Astronomers faced an uncomfortable question. Where do you actually draw the boundaries between cosmic structures? Consider Laniakea, our supercluster, our cosmic home. It spans 500 million light-years and contains roughly 100,000 galaxies. We thought it was an island unto itself, a gravitational kingdom. But Laniakea isn't falling toward itself. It's not even falling toward the Great Attractor first. It's falling toward Shapley, which means Laniakea might not be what we think it is at all. Some astronomers argue that Laniakea remains distinct because galaxies within it flow toward the Great Attractor as an intermediate waypoint. Others counter that if Shapley's gravity reaches into Laniakea and influences everything within it, then Laniakea is simply a tributary, a smaller valley feeding into a much larger one. Imagine water flowing across a landscape. Each stream carves its own small valley where water collects and swirls. The Great Attractor is the lowest point in that small valley. Water spirals there. But these small valleys don't stand alone. They feed into a greater valley, a master valley, Shapley. Eventually, all the water, from every small stream, every tributary, drains toward that main basin. Laniakea isn't a separate island. It's one small valley among many, all destined to empty into the same cosmic reservoir. The numbers make this visceral. Laniakea's basin of attraction? Massive. Shapley's basin? Try 10 times larger. Not 10 times the diameter, 10 times the volume. Think about what that means. If you double a sphere's radius, its volume doesn't double. It multiplies by 8. If you triple the radius, it multiplies by 27. Shapley's Basin has roughly twice the radius of Laniakea, 8 to 10 times the volume. That's the scale of the difference between our supercluster and the thing that owns it. Yet here's what truly haunts cosmologists. We've only mapped galaxy motions out to about 1 billion light-years. The universe extends over 13 billion light-years in every direction. That means we're navigating blind in most of it. If something as unimaginably massive as Shapley can tug on galaxies from 1 billion light-years away, what else lurks beyond our survey limits? What other structures, even more colossal, might be pulling on the things we can actually see? What hierarchies might nest within hierarchies, structures within structures, across scales we haven't yet dreamed of? The universe just revealed one layer of itself, but there could be infinite layers waiting, and every layer we discover only raises a more terrifying question. Are we still falling? Or have we always been falling, and we're only now beginning to understand the true depth of the pit? The Shapley supercluster, a cosmic monster we're being pulled into. We live inside a cosmic monster, and we didn't even know it was there. Hidden beyond the visible edge of our galactic neighborhood lies the Shapley supercluster, a gravitational titan so massive that it's warping the fabric of space itself and dragging our entire galaxy toward its center. But here's the thing, we can't even see most of it. The dark matter alone, lurking invisibly throughout this structure, contains more mass than every star we can observe combined. The exact numbers? They're still a mystery. Distant galaxies hide beyond the reach of our telescopes, swallowed by dust or buried behind the glare of brighter objects in the foreground. But surveys suggest hundreds of thousands of massive galaxies populate this basin, along with millions of smaller dwarf galaxies. Each one contributes its own gravitational pull. Each one feeds the cosmic current flowing toward the center, and at that center lies something truly terrifying. The Shapley core is a cosmic traffic jam of apocalyptic proportions. Imagine multiple massive galaxy clusters, each one containing thousands of galaxies, all crammed into a region of space too small to hold them. These clusters don't bounce off each other like billiard balls. Instead, they pass straight through one another. But their gravitational fields don't pass through anything. They collide violently, pulling and distorting each other's shapes. Some clusters are actively merging right now, slamming together at speeds of millions of miles per hour. When they do, the energy released is almost incomprehensible. It heats the gas between them to temperatures exceeding 100 million degrees Fahrenheit. Stars from different clusters get torn apart and mixed together. Gas clouds collide and shock heat to plasma. Dark matter halos overlap and send each other's orbits careening out of control. It's chaos on the largest scale the universe allows, and we can see it. X-ray telescopes peer into Shapley and detect an eerie glow, brilliant, almost beautiful, radiating in high-energy light. That glow is the death cry of 1 billion collisions. It's the hot gas between galaxies, superheated by the energy of gravitational violence playing out across millions of light years. The atoms in that gas are so violently agitated that they've torn apart completely. Electrons rip free from nuclei. The gas becomes plasma, the fourth state of matter, where charged particles move independently, filling the space between clusters like a web of incandescent fire. This plasma contains more mass than every visible star in every galaxy combined. But Shapley doesn't stop at its core. Filaments of galaxies stretch outward like tentacles, extending far beyond the crowded center. These filaments are highways made of dark matter, tracing the invisible web that underlies all cosmic structure. Where filaments intersect, galaxy clusters form. Where they stretch across empty space, galaxies string out in long, thin chains. It's a spider web on a scale so vast that Laniakea, the galactic supercluster we thought we belonged to, is just a single thread in a much, much larger tapestry. This discovery shattered cosmological expectations. According to our models of how the universe works, there hasn't been enough time since the Big Bang for gravity to build something this enormous. Structures like Shapley should still be assembling themselves, still in their infancy. Yet here it stands, already massive, already dominant, already pulling on everything around it. Some physicists suggest Shapley formed earlier than it should have, born from unusual conditions in the early universe. Others wonder if dark matter behaves differently than we assumed, allowing gravity to work faster. A few scientists are asking the harder question. Maybe our theory of how cosmic structures form is incomplete. Maybe we're missing something fundamental about gravity, about dark matter, about how the universe organizes itself on its largest scales. The debate continues, but one thing is certain. Shapley is real. It's incomprehensibly massive, and right now, it's pulling on us. The Milky Way is flowing toward this cosmic monster, carried along by gravitational currents we can't see or escape. We're being drawn into the Shapley supercluster, and we're just now beginning to understand what that means. We're falling toward it. All of us. The Milky Way, Laniakea, the Great Attractor, hundreds of thousands of galaxies swept up in the same cosmic current, tumbling through space like leaves caught in an invisible river. And here's the terrifying part. If Shapley is 10 times larger than we ever imagined, what else is out there? What other colossal structures are pulling at us from the darkness? But galaxies don't just fall. They also flee. Between the massive structures like Shapley and Laniakea lie voids, enormous regions of space, mostly empty, with very few galaxies scattered through them. Now, you might think a void is nothing, absolute vacuum. But that's wrong. These voids contain dark matter. Just less of it, much less. And that deficit, that absence, creates something unexpected, something that acts like a repeller. Picture it this way. Gravity pulls toward mass. That's its job, but in a region with less mass, there's less pull inward, less attraction toward the center. So what happens? The pull shifts. It points outward, toward the massive structures surrounding the void. Galaxies near a void's edge feel gravity yanking them away from the empty space, pulling them toward the walls where matter clusters thick and dense. The void doesn't actively push. It simply fails to pull. And in a universe drowning in gravitational forces, that failure becomes a shove. One of these structures is the dipole repeller. It's real. It's confirmed. A vast void sitting directly opposite from Shapley, on the far side of the Milky Way. While Shapley pulls us forward with its enormous mass, the dipole repeller pushes us from behind. They're locked in a cosmic tug of war, and we're caught in the middle. Shapley pulls. The dipole repeller pushes. The combined effect accelerates our motion far more than either force alone could ever achieve. And it doesn't stop there. The Great Attractor pulls from yet another direction. Other structures pull and push from angles we're still mapping. The Milky Way's true motion, our actual trajectory through space, is the sum of all these forces. It's a complex vector, a mathematical result of gravitational influences stretching across 1 billion light-years. We're not moving because of one thing, we're moving because of everything. But here's where it gets truly strange. Galaxies caught between these major structures feel the chaos of it all. They experience pulls from multiple directions at once. Their motion becomes unpredictable, chaotic. They're navigating a gravitational landscape more complex than any terrain on Earth. Some fall toward one attractor, others toward a completely different one, and a few, the rare, lucky few, sitting exactly balanced between competing gravitational forces, barely move at all. They hover in a precarious equilibrium, held in place by forces that nearly cancel each other out. The boundaries between these zones of influence aren't sharp dividing lines. They're fuzzy, contested regions where the tug of war is most intense. Galaxies here can switch allegiance. They might be pulled toward one attractor, then slowly drift toward another as the cosmic mass distribution shifts and evolves over billions of years. Think of Earth's watersheds. Rain falls on a mountain ridge. One side flows to one river system. The other side flows to a different one. The ridge marks the boundary. But the ridge isn't a razor's edge. It's a gradual transition where a single raindrop might tumble one way or the other, depending on the subtle contours of the land. Cosmic watersheds work the same way, except the terrain isn't rock and soil. It's curved space-time itself, and the water isn't rain. It's galaxies, falling through gravitational fields for billions of years. We're lucky. The local group sits in a relatively simple part of this landscape. The forces pointing at us are neat, aligned. They stack like dominoes, all pointing the same direction. We feel a strong pull from the Virgo cluster, which is part of Laniakea, which flows toward the Great Attractor, which falls toward Shapley. All of it points the same way. For now, we fall together. Somewhere out there in the cosmic darkness, galaxies are caught in an invisible war. Not all of them are falling toward a single attractor. Some face an even stranger fate, pulled simultaneously by two massive gravitational forces, each tugging in perpendicular directions. These galaxies don't fall straight. They can't. Instead, they trace curved paths through space, caught in a gravitational compromise, pulled by both masters yet enslaved to neither. This tug of war didn't begin yesterday. It began nearly 14 billion years ago, moments after the Big Bang itself. In those earliest moments, the universe wasn't perfectly uniform. There were wrinkles, infinitesimal variations in density, barely noticeable differences between one region and another. But the universe rewarded density. Wherever matter was just slightly more concentrated than average, gravity pulled harder. More matter arrived. The region became denser still. Gravity strengthened. More matter came. A feedback loop was born. Over billions of years, these microscopic fluctuations exploded into the colossal structures we see today. Superclusters, galaxy clusters, the cosmic web itself. All born from cosmic imperfections no larger than a grain of sand. And that tug of war, it's still happening. Right now. Attractors pull, voids repel. Galaxies fall through an invisible landscape shaped by forces they cannot escape. This will continue, pulling and pulling and pulling for trillions of years into the future, but not forever. There's something else out there, something even more powerful than gravity itself. Dark energy, a mysterious force that isn't pulling matter together. It's pushing it apart, accelerating the expansion of the universe. As the eons pass, dark energy will grow stronger and stronger, while gravity grows weaker and weaker. Eventually, the basins of attraction will shatter. The cosmic web will tear apart at the seams. The tug of war will end, not because one side triumphed, but because the rope itself will snap under the weight of infinity. For now, though, the battle rages on. Right now, as you listen to this, the Milky Way is falling through the cosmos. We're caught in currents we cannot resist, pulled by forces we cannot defy, toward destinations we may never reach. We are passengers on a galactic ship with no control over the wheel. But here's the staggering part. Everything that pulls us through space, every attractor, every gravitational current, every structure that shapes the cosmos, is built on something we cannot see. 85% of all matter in the universe is invisible. Dark matter. It doesn't shine. It doesn't reflect light. It doesn't interact with light in any way we can detect. Shine a flashlight at it, and the light passes right through, untouched. Yet this invisible substance commands the largest structures in existence. Its gravity shapes galaxies. Its presence holds galaxy clusters together. Its influence sculpts the cosmic web itself. Think of dark matter as the skeleton beneath the skin. You see the skin, the visible galaxies, the glowing gas clouds, the brilliant stars. But underneath, hidden from sight, lies the framework, the structure, the bones that hold everything together. Without dark matter, galaxies would tear themselves to shreds. Stars near the edges would fly off into the void at tremendous speeds. Clusters would dissolve into isolated galaxies. The cosmic web would never form. Stars might not even exist because the density variations needed to trigger structure formation would have been too small to grow in the time available since the Big Bang. We know this because the evidence is overwhelming. Galaxies spin too fast. Stars at their outer edges move at nearly the same speeds as stars at their centers. By all rights, those outer stars should be moving much slower. They should be drifting away. But they're not. Something invisible holds them in place. Something massive. Something dark. Light itself betrays the presence of dark matter. When light from distant galaxies passes near massive objects, it bends. Gravitational lensing. We can measure how much the light bends and calculate how much mass caused the deflection. The answer shocks us every time. There's far more mass there than visible matter can explain. Entire galaxies worth of mass that doesn't shine. Even the most ancient light in the universe tells this story. The cosmic microwave background, radiation from just 380,000 years after the Big Bang, carries patterns imprinted by gravity. Those patterns reveal how matter was distributed in the infant universe. And those patterns make sense only if dark matter dominated the cosmos back then, just as it does today. In the Great Attractor region, the disparity is almost absurd. For every kilogram of stars and gas, every kilogram of normal matter that we understand, There't roughly 6 kilograms of dark matter. Invisible, untouchable, yet absolutely real. This dark matter forms the gravitational wells where galaxies fall. The visible structures we observe, the blazing galaxies, the glowing nebulae, the entire cosmic web, are nothing but bright foam floating on an ocean of invisible mass. Beneath everything we see lies a realm of darkness that dwarfs the visible universe in magnitude. And here's the crucial difference. Dark matter doesn't behave like normal matter. Normal matter collides. It radiates energy. It cools and condenses and clumps together, forming dense structures like stars and planets. Dark matter does none of this. It doesn't collide. It doesn't cool. It doesn't condense. Instead, it spreads out. It forms vast, diffuse halos surrounding galaxies and clusters, stretching across volumes so enormous they defy comprehension. We cannot see it. We cannot touch it. We cannot understand what it is. And yet, without it, we would not exist. These dark matter halos don't just exist in isolation. They overlap. They merge. And when galaxy clusters collide, they create something extraordinary. The gravitational scaffolding of the entire cosmic web. Run a simulation on a supercomputer. Start simple. Fill the universe uniformly with dark matter and normal matter. Then let gravity do what it does best. Pull everything together. Fast forward billions of years. What emerges is stunning. It matches our universe almost perfectly. Filaments form, connecting dense nodes like threads in a vast web. Voids open up between them, creating cavernous empty spaces. Galaxy clusters grow at the nodes, dense junction points in the cosmic structure. And none of it, makes sense without dark matter in the equations. Look at the real universe. Galaxies are streaming toward the Great Attractor. The Laniakea supercluster is moving in strange patterns. The Shapley concentration exerts an inexplicable pull. But the moment you add dark matter to your calculations, everything clicks into place. The masses work. The velocities check out. The gravitational fields match the predictions exactly. Dark matter isn't just a convenient placeholder for what we don't understand. It's essential. It's the missing piece that transforms the universe from an unsolvable puzzle into a coherent story. But here's the problem. We still have no idea what dark matter actually is. The leading theory suggests it's a particle, something entirely new to physics, something that barely interacts with normal matter at all, touching it only through gravity's invisible hand. Dozens of experiments around the world are hunting for these ghost particles right now, trying to catch them as they pass through Earth. They use sensitive detectors buried deep underground, shielded from cosmic rays, waiting in the silence for something to collide. And so far, nothing definitive. Dark matter remains invisible, its nature unknown, its properties a mystery, except for one undeniable fact: it has mass. And mass warps space. Mass creates gravity. We can map this invisible scaffold using something called gravitational lensing. Imagine light from a distant galaxy traveling across billions of years to reach us. On its journey, it passes through regions thick with dark matter. That gravity bends the light, distorting it like a lens, warping its path. By the time it arrives at our telescopes, the light is bent, twisted, telling us a story. and astronomers have learned to read that story. They measure these distortions. They reconstruct the landscape of dark matter beneath, and the maps they create are breathtaking. A web-like pattern of dark matter. Dense nodes connected by thin filaments, spreading across the observable universe. Exactly as the simulations predicted. Every galaxy sits embedded in this dark matter halo. Every supercluster is anchored to it. The visible universe, the stars, the planets, everything we can see with our eyes or our telescopes, amounts to barely 5% of all the mass in the cosmos. The other 95%? Dark matter and dark energy, invisible, intangible, utterly beyond our direct reach. We know they exist only by watching how they bend and pull the visible universe around them. And that should unsettle you. We are being pulled across the cosmos by something we cannot see, made of something we do not understand, toward a destination we cannot predict. The Great Attractor is pulling us. The pull is real. The force is genuine, but the thing doing the pulling remains mostly dark, mostly mysterious, mostly locked away from our instruments and our knowledge. We're passengers on a cosmic journey, steered by invisible hands, moving toward an uncertain future. But the cosmic web isn't made of scattered clusters. The largest structures in the universe are walls. Picture this: a sheet of galaxies stretching for 500 million light years. Impossibly thin, impossibly wide. A barrier of matter separating the cosmic voids on either side. The Great Wall, discovered in the 1980s, was our first glimpse of these titans. Over 500 million light years across, tens of thousands of galaxies, a boundary marking the edge of our cosmic neighborhood. But then something even more massive was found. In 2003, astronomers mapping the distant universe discovered the Sloan Great Wall, a filament of galaxies stretching 1.4 billion light years across space. A structure so large, so impossibly vast, that it shouldn't even exist according to our best models of how the universe works. The universe was supposed to be simpler than this. It wasn't. Imagine a distance so vast that light itself becomes sluggish. A beam of light fired from one end of a cosmic structure would spend 1.4 billion years in transit. When that light began its journey, Earth's oceans were just forming. By the time it arrives at its destination, entire civilizations might have risen and fallen on distant worlds. Yet this isn't even the largest structure we've discovered. Welcome to the cosmic web, and the problem that's keeping cosmologists awake at night. The Sloan Great Wall isn't a solid barrier. It's something far more elegant. A connected network of superclusters, filaments, and walls, all threaded together by invisible strands of dark matter. And it exists because of a simple principle. Matter doesn't spread randomly through space. It accumulates at the edges. Imagine soap bubbles pressed tightly together. The soap film doesn't exist uniformly. It concentrates where bubbles touch, creating an interconnected network of surfaces. The universe works the same way. Between the cosmic voids, those vast empty chambers of space, galaxies cluster and accumulate. Along these boundaries, density peaks. A web emerges. These aren't solid walls. Light passes through them. Galaxies flow through them. They're simply regions where the universe decided to pack matter more densely than the spaces around them. But their existence tells us something profound. After the Big Bang, the universe wasn't perfectly smooth. Tiny variations in density, ripples smaller than atoms, were imprinted into space itself. Those quantum whispers should have been insignificant. Instead, they became everything. Over billions of years, gravity did its work. Dense regions grew denser, empty regions grew emptier. A foam-like pattern emerged, and that pattern gave birth to the cosmic web we see today. The normal wall spans more than 100 million light-years and anchors the structure closer to us, part of the Great Attractor, a region where gravity is pulling our entire supercluster inward. Galaxies along these walls don't drift aimlessly. They fall. They move at tremendous speeds, drawn toward the densest nodes where gravity's grip is strongest. These walls are the edges of gravitational basins, the boundaries where one attractor's influence yields to another's. On one side, galaxies tumble toward Laniakea. On the other, they fall toward neighboring structures. The walls themselves are caught in the middle. Densely packed galaxies suspended between competing gravitational pools, slowly being sorted into different cosmic destinies. Then came 2020, and astronomers unveiled a discovery that rewrote the maps. The South Pole Wall, a structure comparable in size to the Sloan Great Wall itself, sprawling across billions of light-years, had been hiding in plain sight. Part of it was obscured by the zone of avoidance, the dusty region of our own galaxy that blocks our view. Another part simply lay in the southern sky, where fewer telescopes looked. When researchers finally used advanced distance-measuring techniques to pierce through the haze, they found a cosmic giant in our backyard. Stop and think about what this means. The universe's largest structures, walls spanning billions of light-years, aren't rare anomalies. They're not flukes. They're fundamental. They're the basic grammar of how matter organizes itself on the grandest scales. We don't live near one of these walls. We live inside a cosmic foam, surrounded by them, enclosed by them, defined by them. But here's where the story gets troubling. Those walls were born from quantum fluctuations. In the first fraction of a second after the Big Bang, tiny variations in density, smaller than atoms, rippled through the newborn universe. The Big Bang's expansion didn't erase them. It amplified them. Over 13.8 billion years, gravity took those microscopic whispers and stretched them into structures spanning billions of light-years. The walls we see today are the direct descendants of those primordial ripples, grown to cosmic proportions. Except something doesn't add up. Gravity can only work at the speed of light. Information can only travel so fast. In 13.8 billion years, light can only journey a certain distance through space. Structures much larger than that distance should be impossible. Yet they exist. The walls are too vast. The universe isn't old enough. There hasn't been enough time for gravity to assemble matter into structures this enormous. The cosmologists know it. The data screams it, and no one has a convincing answer yet. We're living inside a cosmic mystery, surrounded by walls that shouldn't exist, in a universe that's playing by rules we don't fully understand. The Cosmic Void Mystery. The universe has just revealed one of its deepest secrets, and it doesn't match what we thought we knew. Astronomers have discovered massive walls of galaxies, structures so enormous they break our mathematical models. Either the models are fundamentally wrong, or the early universe expanded in ways we've completely misunderstood. Everything we thought was settled is suddenly uncertain again. But here's the strange part. The universe isn't mostly made of galaxies. It's made of nothing. Not metaphorically. Measured, undeniable, nothing. If you randomly selected a point in space right now, the odds are staggering that you'd land in absolute emptiness. A void, a region spanning hundreds of millions of light years, containing almost no galaxies at all. Some voids are bigger than Laniakea, our local supercluster, and while these cosmic deserts might hold a dozen galaxies, the dense walls surrounding them hold thousands. You might think voids are just accidents of cosmic chance. They're not. They're the result of a process that started billions of years ago and never stopped. In the young universe, some regions were just slightly less dense than others, just a tiny bit emptier. But that tiny difference triggered a chain reaction. Gravity in the denser surrounding regions pulled matter inward. As matter flowed out of the underdense areas, those regions lost gravitational pull. With less gravity to hold on to what was left, even more matter escaped. It became a runaway collapse. Not of the void into itself, but of matter fleeing the void entirely. Over billions of years, this accelerated. Voids grew larger and emptier. Their walls grew denser and denser. The universe began sorting itself. Matter concentrated into thick filaments and sheets, while vast empty chambers expanded between them. But here's where it gets fascinating. Voids don't just sit there empty. They push, not with any force you can feel or measure directly. They push through absence, through the sheer lack of gravity pulling inward. Imagine standing at the bottom of a valley between two mountains. Both mountains pull you with gravity, but they pull in different directions. The valley doesn't push you up. The mountains just pull you toward their slopes. The valley's emptiness creates an imbalance. Cosmic voids work exactly the same way, except across mind-bending distances in 3 dimensions. The dipole repeller is one of the largest known void structures. It spans roughly 300 million light-years in the direction opposite from Shapley, relative to our position in the galaxy. That's incomprehensibly vast, and it contains far, far fewer galaxies than it should. This deficit of mass creates an effect that looks like repulsion. Galaxies near the dipole repeller's edges feel more gravitational, pull from dense structures on the far side than from the empty void nearby. The imbalance is real. It's measurable, and it's pushing galaxies away from the void's center. Astronomers have confirmed this through detailed mapping of galaxy velocities. Galaxies near the dipole repeller are moving away from it faster than cosmic expansion alone would explain. They're not just drifting apart. They're actively being accelerated by the gravitational imbalance the void creates, and our galaxy caught between two forces. Shapley pulls us one direction. The dipole repeller pushes us another. Together, they accelerate the Milky Way faster than either could alone. Think of it like rowing a boat on a river. The current pulls you downstream toward the ocean, but there's a wind at your back, pushing you in the same direction. You move faster than the current alone would carry you. We are that boat. Shapley is the ocean pulling us. The dipole repeller is the wind at our back. The boat is void, discovered in the 1980s, is a haunting example of cosmic emptiness. It stretches about 330 million light-years across, and it contains only around 60 galaxies. A region that size should contain over 2,000. That's not a minor deficit. That's a near total absence. For decades, astronomers were baffled. How could such a vast region become so devoid of matter? Where did all the galaxies go? The answer lies in the feedback loops of cosmic structure formation. Small underdensities in the early universe expanded faster than average regions. As they expanded, matter flowed outward toward denser surroundings. This outflow made them even less dense. Lower density meant weaker gravity. Weaker gravity meant even faster expansion. The process fed on itself exponentially until entire regions were nearly empty, with all the matter squeezed into the walls surrounding them. Galaxies that happen to form inside these voids live solitary existences. No neighbors, no nearby gravitational companions. Just an isolated galaxy in an ocean of black, empty space. This revelation changes everything. The large-scale structure of the universe isn't random. It's shaped by these colossal empties just as much as by the dense walls. The voids are architecture. They redirect galactic motion. They influence cosmic evolution. They exist at scales that dwarf anything we can experience or even fully comprehend. And they remind us that the universe is far stranger, far more structured, and far more mysterious than we ever gave it credit for. The hidden architecture of the universe. Imagine a universe that looks nothing like what we thought, not a smooth, evenly distributed sea of galaxies, but a cosmic foam. Bubbles of emptiness surrounded by walls of galaxies. This is the real universe we inhabit. In these empty voids, galaxies are abandoned. They drift in isolation, cut off from the gravitational currents that shape the rest of the cosmos. They don't collide with neighbors. They don't experience the cosmic crashes that trigger explosive starbirth. The result? Void galaxies are smaller, bluer, younger. They've evolved on their own timeline, in their own way, because nobody's pushing them around. But the real drama doesn't happen in the voids. It happens at the boundaries, where emptiness meets structure, where cosmic walls collide with cosmic voids. Picture yourself standing in a river's rapids. Water rushes at you from behind, while the current pulls you forward. You're caught between two forces, accelerating violently toward the rapids. This is what happens to galaxies trapped in transition zones. They're squeezed by gravity from all sides, moving millions of miles per hour relative to the universe's expansion. We call these movements peculiar velocities. And right now, our own Milky Way is caught in this cosmic squeeze, accelerating under the combined gravity of multiple structures, pushing and pulling us simultaneously. But here's the cruel part. This will only intensify. Dark energy is stretching the universe faster and faster, and it stretches voids most aggressively of all. Empty regions expand at breakneck speed. Dense regions expand more slowly. Over billions of years, the universe will become more extreme. Voids will balloon into vast emptiness. Walls will compress into razor-thin filaments. Galaxies will eventually find themselves completely isolated, trapped on tiny dense nodes separated by billions of light years of absolute nothing. For now, though, we're in a moment of balance. Gravity pulls galaxies toward walls. Walls concentrate galaxies into attractors. The dance continues, ancient and eternal, driven by gravity's relentless grip and the mysterious repulsion of empty space itself. Then, in 2020, something extraordinary happened. while humanity locked itself away from a pandemic, while observatories went dark and silent, astronomers sat at home analyzing decades-old data. And they found something that had been hiding directly in front of us the entire time. A cosmic wall so massive, so influential, that it's been shaping our entire local universe, and we didn't even know it existed. They called it the South Pole Wall. Imagine a cosmic arm made entirely of galaxies, wrapping around our local neighborhood like a celestial embrace. This structure rivals the largest formations ever discovered, and it sits close enough to fundamentally alter our gravitational environment. The densest part of this wall points directly toward Earth's south celestial pole, the southern point of our sky. This is why it remained hidden. Northern observatories can't see it. Southern observatories struggle because thousands of bright foreground stars act like a cosmic glare, drowning out the faint light of distant galaxies. Part of the wall even hides behind the dust and gas of our own Milky Way. To find it required genius and persistence. Instead of photographing galaxies directly through the glare, astronomers used a different tool. They measured something invisible: how light itself changes as it travels through an expanding universe. As the cosmos stretches, it stretches the light waves traveling through it. Light from distant galaxies gets shifted, stretched toward the red end of the spectrum. By measuring this redshift, astronomers could calculate distances. By calculating thousands of distances, they built a three-dimensional map, and that map revealed the truth: a connected structure, a filament of galaxies extending in a colossal arc across 200 degrees of sky, more than half a circle. The South Pole Wall curves from the southern sky, wraps around the edge of our local supercluster, a region we call Laniakea, and extends into the northern sky. At its closest point, this wall approaches within 300 million light-years of Earth. At its farthest, it stretches nearly 500 million light-years away. Thousands of galaxies, all connected by invisible filaments of dark matter, all bound together by shared gravity, all part of one coherent gravitational system. Think of the South Pole Wall as a continental divide for the cosmos. Galaxies on one side flow toward Laniakea and beyond, pulled by the Great Attractor, a region of space so dense, so gravitationally powerful, that entire galaxy superclusters are falling toward it. Galaxies on the other side of the wall flow in completely different directions, toward entirely different attractors, in different regions of the universe we haven't even explored yet. We are caught between these great structures, shaped by their gravity, pulled by their influence, and we're only now beginning to see them. The universe's hidden monsters. Picture this. We've spent over a century staring at the cosmos. We've built telescopes so powerful they can see light that's been traveling since before Earth existed. We've cataloged millions of galaxies across the entire sky. We've mapped the universe, or so we thought. Then astronomers stumbled upon something impossible. A structure so massive, so close to us, that it had been hiding in plain sight the entire time. We call it the South Pole Wall, and its discovery forces us to confront a deeply unsettling truth. We don't actually know our cosmic neighborhood. The South Pole Wall is a boundary in the gravitational landscape. Think of it as a ridge separating different valleys in a cosmic terrain. It's comparable to the Great Wall of Sloan, one of the largest structures in the observable universe, yet we missed it. How? Because mapping the universe from inside it is extraordinarily difficult. We have blind spots. We have biases. We miss what we're not looking for. But here's where it gets stranger. The South Pole Wall isn't isolated. It connects to something even larger. The Shapley supercluster and galaxies along the wall don't drift randomly through space. They flow in organized streams, pulled downward like water flowing into a drain. They're falling towards Shapley, just as our own galaxy, Lanakia, falls toward the Great Attractor. If the South Pole Wall is truly part of Shapley's gravitational basin, then Shapley is far more massive than we ever realized. The structure would stretch across more than 1 billion light years. But here's the problem. We're not certain. The distances we've measured have huge error bars. Some galaxies we think are part of the wall might actually be in front of it or behind it, just accidentally aligned like a cosmic illusion. We need better observations. We need more data from the southern sky. We need to see clearly, and that's just the beginning of the mystery. Because if the South Pole Wall really exists, at the scale we think it does, it shouldn't. According to our best models of how the universe works, structures this massive shouldn't have had enough time to grow since the Big Bang. We're talking about something that challenges the very foundations of our understanding of cosmic architecture. Think about it. The universe began with quantum fluctuations, tiny, almost imperceptible ripples in the fabric of space-time. Gravity amplified these whispers over billions of years. But there's a limit to how large these structures can grow. The South Pole Wall appears to exceed that limit. It exists. We've confirmed it through observations, yet it shouldn't. This forces us to ask, what are we missing about how the universe works? The wall reveals something more. Lanakia, our local group of galaxies, isn't an independent island drifting alone through the cosmos. We're part of a vast network. We're connected to the South Pole Wall, which connects to Shapley, which connects to even larger structures we're only beginning to perceive. And the most unsettling realization, there could be even bigger structures waiting in regions we haven't surveyed carefully. Or worse, waiting in regions we simply cannot observe. Now, let's talk about our fall. The Milky Way isn't floating peacefully through space. We're plummeting toward the Great Attractor at 1.3 million miles per hour. That's 600 kilometers every single second. At that speed, you could circle Earth's equator in just 67 seconds. So here's the question. How long until we arrive? The math seems straightforward. The Great Attractor lies 250 million light-years away. Divide distance by speed. Simple. Except the universe doesn't work that way. Space itself is expanding. Dark energy, a mysterious force we barely understand, is accelerating this expansion. The Great Attractor isn't sitting still, and we're not falling in a straight line toward a stationary target. We're falling through a universe that's actively stretching, pulling distance between us and our destination. Imagine walking on a treadmill. If you walk forward at exactly the same speed, the belt moves backward. You stay in the same place. You can run forever and never get anywhere. That's closer to what's happening to us. As we fall toward the Great Attractor, the expansion of space pushes it away. We're making progress, but the universe is working against us. At our current velocity, with no changes in direction, and assuming the target never moved, we would need 400 billion years to arrive. But that number is almost meaningless. Space expands. The Great Attractor accelerates away from us. Our trajectory curves. And we don't even know the exact distance. Our measurements have uncertainties that could add or subtract millions of light years. The deeper we dig, the more we realize how little we actually understand. We've mapped millions of galaxies. We've built the most powerful telescopes humanity could imagine. We've spent generations studying the cosmos. And yet, the universe keeps astonishing us. Enormous structures hide in regions we've already looked. Features we never predicted appear right in front of us. And the more we learn, the more we confront a humbling truth. We are living inside a mystery we're only beginning to comprehend. The cosmic journey will never complete. Imagine you're walking on a treadmill. If the belt moves slower than you, you make progress. If it moves faster, you're stuck, walking forward but going nowhere. Now imagine that treadmill spans billions of light years, and you're riding on it as a galaxy falling towards something called the Great Attractor. Right now, we're falling. The Milky Way is being pulled through space by this massive gravitational anomaly lurking in the distance. Gravity is relentless, constant, inevitable. But there's a problem. The Great Attractor is so far away that cosmic expansion is stretching the space between us, adding distance faster than we're falling. It's like trying to reach someone while they're slowly backing away. And then there's dark energy, the universe's most maddening mystery. Dark energy doesn't just expand space, it accelerates that expansion. The older the universe gets, the faster it stretches. Imagine throwing a ball upward. Gravity pulls it down, but your initial throw carries it higher. Eventually, gravity wins. The ball stops rising and falls back to Earth. We're in that rising phase right now, still approaching the Great Attractor because of our current motion through space. But dark energy is our gravity. It's gathering strength with every passing billion years. And when it finally dominates, perhaps within 10 to 15 billion years from now, it will stop our infall. Then it will reverse our trajectory entirely. We'll start being carried away by the expansion of space itself. But here's where it gets truly strange. The Great Attractor isn't sitting still. It's being pulled towards something even larger, the Shapley supercluster. So even if we somehow reached the Great Attractor region, we wouldn't stop there. We'd continue falling, carried along like passengers on a cosmic train with no final destination. The universe is a hierarchy of gravitational structures, each nested within the next. Our local group, the Milky Way and Andromeda, is gravitationally bound. We will merge in about 4 billion years. Our combined galaxy will then fall toward the Virgo cluster, which is also gravitationally bound. That merged structure will fall toward the Great Attractor region. These local scales operate independently of dark energy's influence. They follow gravity alone. But imagine a river flowing toward the sea. You start high in the mountains, riding the current downstream. The river widens as you descend, moving slower, but still carrying you forward. You pass through deltas where the river splits into channels, each one drawing you closer to the ocean. Then you notice something terrifying. The tide is going out. The ocean isn't just far away anymore. It's receding faster than the current can carry you. You'll never actually reach open water because the water itself is draining away. That's our fate. Here are the timescales. The Milky Way and Andromeda merge in about 4 billion years. The combined galaxy reaches the Virgo cluster region in another 5 to 10 billion years. The journey toward the Great Attractor might take 20 billion years or more. But dark energy will dominate in just 10 to 15 billion years. Long before we arrive, the expansion of space will overcome gravity's pull entirely. We'll never get there. For decades, astronomers have mapped the cosmos. They've traced gravitational flows across hundreds of millions of light years. They've identified the Great Attractor and measured its pull on our motion through space. They've invested careers in understanding our destination, our cosmic address, where we're headed in this vast and expanding universe. And the answer is nowhere. We're passengers on a journey with no arrival, travelers approaching a destination we will never reach, pulled by forces that will ultimately be overwhelmed by the expansion of space itself. There's a cruel poetry to it. The universe doesn't care about our destination. It only cares about the journey, the distance we fall, the structures we merge with, the gravitational embrace of scales too vast for us to truly comprehend. We are falling toward infinity, but infinity is moving away from us faster than we can fall. In 1998, astronomers made a discovery that would reshape our entire understanding of this cosmic drama. They observed distant supernovae and found something impossible. The expansion of the universe wasn't slowing down, it was accelerating. That discovery earned them the Nobel Prize, and it fundamentally changed our answer to the question of where we're going. We're not going anywhere at all. In 1998, astronomers made a discovery that shattered everything we thought we knew about the universe's destiny. They were hunting distant supernovae, stellar explosions so bright they could serve as cosmic measuring sticks. These explosions let us calculate how far away galaxies really are. And when they looked at the data, something terrifying stared back. The universe's expansion wasn't slowing down. It should have been. Gravity pulls everything inward. So logically, the cosmic expansion left over from the Big Bang should be grinding to a halt. Instead, it was accelerating, speeding up. The universe was being pushed apart by something no one had ever directly observed. Something working against gravity itself. And it was getting stronger. They called it dark energy. Not because they understood what it was, they didn't. They called it dark energy because they needed a name for the invisible force operating beyond our direct view, hidden in the darkness of the cosmos. And here's what makes it terrifying. Dark energy is winning. Gravity pulls things together. Dark energy tears them apart. And dark energy dominates the universe. 70% of everything, all the energy that exists, is dark energy. 25% is dark matter, invisible, but at least it has mass. Normal matter, the stuff you're made of, the galaxies, stars, and planets we can actually see and touch, that's just 5%. 5%. The universe is almost entirely made of things we can't see and don't fully understand. This rewrites everything we thought we knew about the Great Attractor and our place in the cosmic web. Gravity builds. It pulled galaxies together over billions of years, creating clusters, then superclusters, towering structures of matter stacked across incomprehensible distances. But dark energy destroys. It pushes space apart, stretching the cosmic fabric, working tirelessly to scatter what gravity spent eons assembling. These two forces are locked in a cosmic arm wrestling match, and the outcome depends entirely on scale. Close to home, gravity still dominates. The Milky Way will collide with Andromeda. Our local group will hold together. The Virgo cluster won't fly apart. But zoom out further. Look at the largest structures in the universe, and dark energy takes over. The supercluster we call Laniakea will disperse into the void. The Great Attractor's grip will weaken. Even Shapley's Basin, a massive collection of thousands of galaxies, will eventually tear itself apart. For the first few billion years of cosmic history, gravity was in control. Structures grew larger, denser, more impressive. But then, dark energy began to take the upper hand. Now there's a limit to how large any structure can grow. Dark energy will eventually shred it to pieces, push it beyond the breaking point, and the Great Attractor sits right at this cosmic frontier, right where gravity's control begins to fail. Within the Great Attractor's influence, gravity still wins. Clusters remain bound. Galaxy groups hold together, but the larger currents of the universe, the cosmic rivers carrying galaxies toward the Great Attractor, are about to reverse. Galaxies that are currently falling inward will slow down, stop, then begin moving outward as expansion accelerates. The entire flow of the cosmic web is turning around. The math confirms it. When cosmologists run simulations, accounting for both gravity and dark energy, the answer is always the same. Superclusters like Laniakea are temporary. They exist right now because the universe is in a transition period. Gravity had just enough time to build them. Dark energy hasn't had quite enough time to destroy them. But it will. Billions of years from now, they'll be gone, scattered across an ever-expanding void, and something even more profound will happen. Galaxies beyond our local group will vanish from view, not destroyed, not consumed, but carried away by the expanding space between us so fast that their light can never reach us again. Light travels at a cosmic speed limit, but space itself expands faster. We'll lose them, every one of them. From our perspective, the universe will appear to shrink. The visible cosmos will contract, containing fewer and fewer galaxies with each passing eon, until only our local group remains visible in the darkness. Everything else will disappear beyond our cosmic horizon, carried away by the relentless push of dark energy, lost to us forever. This makes our moment in time extraordinary, miraculous even. Right now, in this era, in this cosmic instant, we can see the full structure of the universe. We can map the superclusters. We can trace the cosmic flows. We can witness the grand architecture that gravity spent billions of years constructing. We can see the cosmic web in all its glory. Future civilizations, billions of years from now, won't have this privilege. They'll inherit an apparently empty universe, just their own small corner of galaxies surrounded by endless darkness. No evidence that larger structures ever existed. No view of the vast cosmic web that once filled the heavens. That knowledge will be lost to them, available only through records from our era. We are living in the universe's most informative age, and we're running out of time to understand it. The Cosmic Trap. Why the universe will steal the stars. We chase. Imagine a city you could walk to, close enough that you can see the lights, close enough that you're already moving toward it. But every step you take, the road stretches. Every meter you travel, the distance ahead grows longer. Not because you're slowing down, but because space itself is expanding faster than you can move through it. This is the Great Attractor's tragedy. It's a massive gravitational anomaly lurking 250 million light-years away, pulling thousands of galaxies, including our own Milky Way, toward it across the cosmic void. We're approaching it right now. Our galaxies are already in motion, falling through space at incredible speeds. But there's a cosmic catch. Dark energy is winning. Dark energy is the universe's invisible hand, pushing space apart faster and faster with every passing moment. The expansion of space itself accelerates. And here's the brutal truth. At vast distances, expansion adds space faster than gravity can pull things together. The closer structures, nearby galaxies, local clusters, remain reachable. Expansion creeps across small distances, slowly enough that gravity still holds sway. But distant objects, they're already beyond our reach, carried away by the expansion of space like a raft drifting down an accelerating river. The Great Attractor sits in that deadly twilight zone, close enough that we're currently falling toward it, far enough that expansion will eventually overwhelm gravity entirely. In the end, it will slip away from us, carried beyond the edge of forever, on a wave of cosmic expansion we cannot stop. But here's where the mystery deepens. No one knows what dark energy actually is. It's the deepest puzzle in modern physics. Einstein stumbled onto it by accident. When he wrote down his equations of gravity, the mathematical rules that govern the cosmos, he realized something was missing. The equations didn't balance. To fix them, he invented something entirely new: the cosmological constant, a term representing energy inherent to space itself. Energy that does nothing but push everything apart. Then Einstein looked at his own work and panicked. He called it his biggest blunder. He erased it. He decided the universe shouldn't need such a thing. Decades later, astronomers discovered he was right the first time. Space does have this energy. The expansion is accelerating. Dark energy is real. But here's where physics breaks down completely. When physicists use quantum field theory, our best understanding of how reality works at the smallest scales, to calculate what dark energy's strength should be, they get a number. But this number is wrong. Catastrophically, impossibly wrong. It's off by 120 orders of magnitude. That's a 1 followed by 120 zeros. Let me put this in perspective. If you predicted the weight of your car and were off by 120 orders of magnitude, your prediction wouldn't just be wrong. It wouldn't be slightly wrong or very wrong. You'd be wrong by more than the difference between an atom and the observable universe. You'd be off by the kind of margin that doesn't even exist in nature. It's the worst prediction in the entire history of physics, and this failure reveals something fundamental. Something is catastrophically broken. Either quantum field theory, the theory that explains nearly everything we know about matter and energy, is dramatically, fundamentally wrong. Or general relativity, Einstein's theory of gravity that passes every test we throw at it, is missing something crucial. Or we're blind to some entirely new layer of reality we haven't even begun to understand. Dark energy controls the fate of the cosmos. It decides which structures remain bound together and which will eventually disperse into the void. It shapes the destiny of galaxies, stars, and everything we know, yet we're stumbling in darkness, unable to explain it. Now, what exactly is at the center of the Great Attractor that pulls on us so strongly? After decades of intensive observation, mapping the zone of avoidance, that region hidden from view by our own galaxy's dust. Scientists have finally begun to see through the cosmic fog. Radio telescopes and infrared instruments have pierced the veil. They've traced the flows of galaxies across billions of light years, measured their peculiar velocities, mapped their cosmic motions. What they found: not one monster lurking at the center, but many. The Great Attractor isn't a single structure. It's a cosmic mountain range. The heart of it contains multiple massive galaxy clusters packed within a relatively small region of space. The largest is the Norma cluster, containing thousands of member galaxies. Around it lurk other colossal structures: the Centaurus cluster, the Pavo Indus Wall, each a towering mass of gravity and dark matter. Names vary across astronomical catalogs because observations remain incomplete. The dust still blocks our view. But the data converges on one conclusion: this is not a tidy, symmetrical structure. It's chaotic and complex. Between these clusters lies something invisible to the naked eye but screaming with energy: superheated gas. Millions of degrees hot, accelerated to such temperatures by the violent gravitational interactions of the surrounding clusters. This gas glows in X-rays, light we can't see with our eyes, but that space telescopes detect easily. The X-ray signatures reveal everything. The temperature of the gas betrays the strength of the gravitational field. The more massive a region, the deeper its gravitational well, the hotter its gas burns. The X-ray observations confirm it. The Great Attractor region contains an enormous concentration of mass, but the distribution is strange, irregular. The gravitational pull on surrounding galaxies doesn't point to one central peak. Instead, it traces a complex web of multiple dense nodes, each pulling in slightly different directions. It's like a mountain range with many jagged peaks rather than one towering summit. Each peak generates its own gravitational field. The combined effect creates the overall cosmic pull we observe from billions of light years away. And underneath it all, invisible and dominant, lies dark matter. It accounts for 85% of all the mass in this region. The visible galaxies and hot gas we can observe, they're just the 15% foam atop an ocean of invisible substance. Dark matter forms vast halos around and between the galaxy clusters, their influence extending far beyond the visible structures. These halos overlap, creating a smooth gravitational field that extends across millions of light years. A cosmic web pulling everything toward the Great Attractor. We are passengers on a cosmic journey, falling toward a destination we can see but never reach, shaped by forces we cannot explain. Dark energy and dark matter, the two great mysteries that dominate 95% of the universe, remain fundamentally unknown. The Great Attractor pulls us forward, but the expansion of space will eventually carry it away. In the end, gravity will lose, space will win, and everything we chase will vanish into the dark. Picture this: our galaxy is moving, not drifting, moving fast. Across the vast cosmic ocean, the Milky Way and billions of its neighbors are being pulled toward something invisible, something massive, something we can't quite see. We call it the Great Attractor. For decades, astronomers assumed this cosmic monster must be singular, a supermassive black hole, a concentration of exotic dark matter we'd never encountered before. maybe even a bizarre arrangement of black holes locked in cosmic orbit. But nature rarely cooperates with our assumptions. The truth is far stranger. The real culprit isn't one thing at all, it's dark matter. And it's not hidden in some exotic center waiting to be discovered. It's everywhere, distributed across galaxy clusters, woven through the cosmic web, defining the very shape of space itself. The Great Attractor is less a destination and more a location. Think of it this way. Imagine a vast valley between mountains. The valley floor is the lowest point, where water naturally collects and flows. But the valley isn't a thing. It's not an object. It's a feature, a consequence of the terrain that surrounds it. The mountains define the valley by their very existence. The Great Attractor works the same way. Here's the puzzle that cracked it open. The Norma Cluster, the largest structure in the Great Attractor region, contains about 1/10 the mass we originally calculated. Early astronomers estimated we'd need the gravitational pull of 100,000 galaxies to explain what we observe. But when we looked closer, we found only 10,000 galaxies worth of visible mass. The math didn't work. Something was missing. Then came the revelation. The extra pull wasn't coming from the Great Attractor alone. It was coming from Shapley, a massive structure lurking beyond it. Multiple cosmic structures, multiple gravitational anchors, all working together. The Great Attractor isn't a center, it's a node. A junction point where the filaments of the cosmic web intersect. It's the lowest point in our cosmic neighborhood's gravitational landscape, where multiple rivers of matter and energy naturally converge. This isn't speculation. We can prove it when we run simulations of the universe, starting with dark matter uniformly distributed, adding tiny density fluctuations, then letting gravity work for billions of years. We get exactly what we observe. Regions that started slightly denser than average collapse inward under their own weight. Where these filaments cross, nodes form naturally. The Great Attractor emerges from the mathematics like a flower blooming from soil. But here's where it gets interesting. Even after decades of study, the Great Attractor keeps its secrets. 20% of the sky is hidden from us. Not by distance, by dust. The Milky Way's own gas and dust form a veil we call the zone of avoidance, obscuring entire regions of the universe directly behind our galaxy. Radio and infrared light can partially pierce this veil, but incompletely. There could be entire galaxy clusters lurking behind that barrier. Unusual structures we've never encountered. Configurations of mass and dark matter that don't fit our models. The Great Attractor was never discovered by seeing it. It was discovered by feeling its pull, by noticing that galaxies around us were moving in strange ways, their velocities pointing to an invisible source. We traced those peculiar motions back to their origin, like following ripples in a pond back to the stone that made them. So ask yourself, if the Great Attractor, the structure dominating our cosmic neighborhood, the gravitational force bending billions of galaxies toward it, still holds mysteries. After all our observations, what else is hiding in that zone of darkness? What other massive structures lurk beyond our view, pulling on the universe in ways we don't yet understand? What cosmic architecture remains unmapped in the regions we cannot see? This question keeps astronomers awake at night, because for all our technology, for all our telescopes and simulations and clever mathematics, the universe still has the power to surprise us. The darkness remains, and somewhere in that darkness, waiting to be discovered, The cosmos continues its ancient work. The hunt continues. There's a technique that could reveal other hidden attractors, if they're out there, but finding them requires something most astronomers lack: perfect data. You need velocity measurements for galaxies spread across vast regions of sky. You need to know how far away they actually are. You need to untangle local gravitational tugs from the universe's larger scale flows. It's painstaking work. And then there's the zone of avoidance, that cosmic blind spot where our own galaxy's dust blocks our view. But radio telescopes are breaking through that barrier. They've mapped thousands of galaxies lurking behind the zone. What they found? Clusters. Superclusters. Structures that look eerily similar to what we see in the visible universe. The galaxy density back there matches what we find everywhere else. There's nothing obviously special about this hidden region. Nothing except that we can barely see it. Here's the problem, though. Every telescope is blind in certain ways. Radio telescopes find large galaxies rich with hydrogen gas, but miss the smaller, fainter ones. X-ray telescopes spot massive, hot galaxy clusters, but overlook the smaller groups and isolated galaxies. Infrared can pierce through dust better than visible light, yet still struggles in the densest regions. Every tool has blind spots. So could another great attractor be hiding behind that veil? Maybe. If it existed, it would tug on nearby galaxies, leaving telltale signs in their motions. Astronomers have been recording these velocities for decades now. They've found the Great Attractor's fingerprints. They've found Shapley's influence. They've found the dipole repeller, pulling galaxies the opposite direction. No other major anomalies have shown up yet. But yet is the operative word. Surveys are still running. Data keeps accumulating. The universe hasn't finished revealing its secrets. The more unsettling question is this: what if attractors exist where we can actually see, but we still haven't found them? What if something lurks billions of light years away, so distant or so subtle that it's escaped detection entirely? The universe stretches billions of light years in every direction. We've mapped galaxy motions out to about 1 billion light years with reasonable precision. Beyond that, the measurements fall apart. Cosmic expansion, the universe itself stretching, drowns out any peculiar velocities. Separating the two requires distance estimates so precise that our current techniques simply can't deliver them. Imagine trying to map ocean currents. Near the shore, you place buoys, drop instruments, measure everything precisely, move into the open ocean, and your data becomes sparse, uncertain, fragmented. You could miss entire currents simply because you haven't dropped instruments in the right places. You could miss major flows simply by being in the wrong location. The cosmic version is worse. We can't deploy instruments. We're trapped here, on Earth, trying to reconstruct three-dimensional cosmic architecture from a two-dimensional map of the sky and one-dimensional velocity measurements. It's like describing a sculpture by looking at its shadow. Then there's an even more disturbing possibility. Attractors so distant that their light hasn't reached us yet. Our observable universe has a hard boundary, the edge of how far light can travel since the Big Bang. Beyond that cosmic horizon, we see nothing. The light from those regions simply hasn't had time to arrive. But gravity doesn't play by those rules. Gravity's influence travels at light speed, yes, but that doesn't mean we need to see something to feel it. If an enormous structure, a supermassive attractor, existed just beyond our observable horizon, we might detect its gravitational pull before we ever see its light. Is this likely? Probably not. The cosmological principle suggests the universe is roughly uniform on large enough scales. If supermassive attractors lurked just beyond our horizon in one direction, we'd expect to find similar structures in other directions. The universe shouldn't show us favoritism, but it's not impossible. And right now, as surveys expand and technology improves, we're entering an era where we might finally find out. The cosmos still has surprises waiting. We just need to look harder, listen closer, and ask better questions. There's a mystery unfolding above your head right now. The galaxies around us aren't drifting randomly through space. They're flowing, streaming, being pulled by something so massive, so gravitationally dominant, that it's dragging our entire supercluster toward it like a whirlpool in the cosmic ocean. We call it the Great Attractor. But here's where it gets unsettling. We might be missing the whole picture. When astronomers map the motions of distant galaxies, they expect to see chaos, random tugs from different directions. Instead, they find something eerily ordered. Coordinated flows toward known structures like Shapley, toward the Great Attractor itself. But what if we're only seeing part of the gravitational landscape? What if there are other massive structures lurking in the darkness, hidden from our telescopes, still pulling on us from directions we haven't even looked? We've built our entire understanding of cosmic motion on a single, audacious assumption: the cosmological principle. It says the universe looks roughly the same everywhere, no matter where you stand or where you look. And fair enough. The evidence supports it. The cosmic microwave background radiation, the ancient light from the Big Bang itself, appears virtually identical in every direction we observe it. Galaxy surveys show consistent patterns across the sky. Everything points to a universe that's statistically uniform, balanced, fair. Except for one problem. We're making all of this from one vantage point: Earth, at one moment in cosmic time. Now, that's like standing in a single room of an infinite mansion and declaring you understand the entire architecture. If we've overlooked a hidden gravitator, a colossal concentration of matter lurking beyond our detection, then our calculations are fundamentally broken. We think we know where we're going. We've mapped the gravitational currents. We've calculated our velocity, our trajectory. But if there's another massive structure we haven't found, we could be falling toward an entirely different destination. We could be passengers on a cosmic journey we don't actually understand. This is why astronomers never stop searching. They map galaxies obsessively. They measure velocities with increasing precision. They calculate distances using every technique available. Each new observation fills in the blanks. Each discovery adds another piece to an ever more complete picture. And slowly, miraculously, the zone of avoidance, those patches of sky hidden behind the dust and gas of our own galaxy, is becoming less mysterious. New technology is piercing the veil, and maybe, just maybe, someone will find what's been hiding there all along. Another great attractor. Another massive structure pulling on us from a direction we never expected, waiting in plain sight for decades, undetected. But the Great Attractor tells us something far more profound than just where we're headed. It tells us where everything came from. Billions of years ago, in the first fraction of a second after the Big Bang, the universe wasn't uniform at all. It was seething with quantum uncertainty, tiny subatomic fluctuations in density. infinitesimal ripples in the fabric of existence. These weren't mistakes or imperfections. They were everything. As space expanded, those microscopic variations got stretched across the cosmos, like wrinkles on an inflating balloon. And then gravity took over. For billions of years, gravity amplified those primordial whispers into thunderous structures. Tiny density differences snowballed into filaments spanning hundreds of millions of light years. Those quantum whispers became the cosmic web, a vast scaffold of superclusters, walls, and voids that define the universe we see today. The architecture we observe now was written 13.8 billion years ago. The universe's large-scale structure wasn't random. It was predetermined. Gravity didn't create these structures. It simply followed the blueprint, the pattern laid down in that first instant of creation by pure quantum randomness. We're living inside a universe whose entire architecture was decided before the first star ignited. But here's where the story takes a tragic turn. The cosmic web is tearing apart. Dark energy, this mysterious force that makes up 68% of the universe, is accelerating the expansion of space itself. And unlike gravity, which weakens with distance, dark energy's pull gets stronger the further apart things become. Over cosmic time, dark energy will inevitably overcome gravity. Even in the densest regions, even in the cores of superclusters like Laniakea, the Great Attractor will stop attracting. Shapley will fragment. The intricate cosmic web, built over billions of years from quantum chaos, will unravel into isolated, drifting islands of light, separated by voids so vast and expanding so rapidly that no signal could ever bridge them. This is the universe's life cycle, and we're living in its most exquisite moment. Picture 3 phases. The first phase lasted roughly 10 billion years, the era of structure formation, when gravity dominated, when matter clumped together faster than expansion could push it apart. Superclusters formed. Galaxies clustered into groups. Groups clustered into clusters. The cosmic web was being woven. We're in the second phase now, a fleeting transition. Gravity and dark energy are locked in combat, matched in their strength. Structures still exist, still cling together in their cores, but they're beginning to feel the strain of expansion at their edges. Superclusters are bound where they're dense but tearing at their peripheries. It's a brief moment of balance. The third phase will last essentially forever. Dark energy will dominate completely. Expansion will accelerate without limit. Superclusters will disperse. Galaxy clusters will scatter. Individual galaxies will drift apart so far and so fast that even light itself won't be able to carry a signal between them. Eventually, trillions of years from now, even stars will tear themselves apart. Matter itself will be shredded by the expansion of space. The universe will become a graveyard of isolated particles, alone in an infinite darkness. The Great Attractor teaches us something that should give us pause. We're living in a special time, perhaps the only time. Right now, the universe is rich with structure, teeming with complexity, filled with galaxies, connected by gravity and communication. We can see other stars. We can contemplate our place in the cosmos. We can wonder about the structures pulling on us from the darkness. But this era of abundance won't last forever. We're in the golden age of the universe, and we're only now beginning to understand it. The universe is dissolving. Before our eyes, Imagine looking up at the night sky and seeing not just stars, but the skeleton of reality itself. Galaxies aren't scattered randomly. They cluster together. Those clusters link into filaments, and those filaments weave into superclusters, vast structures that dwarf entire galactic neighborhoods. They're held together by gravity, organized by invisible basins of attraction that channel matter across hundreds of millions of light years. We can map this cosmic architecture. We can study it. We can trace its history and predict its future. But here's the unsettling truth. We are the lucky ones. And our luck is running out. Billions of years from now, observers looking up at their sky will see something radically different. They won't see the towering superclusters we observe today. They won't see the Laniakea, the superstructure that contains our own Milky Way. They won't see the Great Attractor, that massive cosmic engine pulling galaxies across unfathomable distances. Instead, they'll see a sparse, nearly empty universe. A few local galaxies scattered in the void. No walls, no filaments, no grand architecture. Just darkness and isolation. The reason? The structures that seem permanent, eternal features carved into the fabric of space-time, are actually temporary. They exist for a finite window of cosmic time. The Great Attractor doesn't exist forever. Neither does Laniakea. They were born billions of years ago from the gravitational amplification of tiny density fluctuations in the early universe. And they're dying. Not quickly, but inevitably. One day, far in the future, they will dissolve completely into the expanding void. We live in the exact moment when these structures are visible. We exist during the brief cosmic window when observation is possible, and some cosmologists find this deeply troubling. It means the universe isn't eternal. It's a temporary phenomenon. We're witnessing one fleeting phase of cosmic evolution, nothing more. But wait, shouldn't this be unlikely? If the universe is so vast and exists for so long, how did we end up here, in this precise moment, able to see these structures? The answer is the anthropic principle. We shouldn't be surprised to find ourselves in a time and place where observation is possible. If the universe were too young, life couldn't have evolved. Stars wouldn't have formed. Chemistry wouldn't exist. If the universe were too old, all the stars would have burned out. Galaxies would have dispersed into an empty, lifeless void. Life and cosmic observation require a narrow window, a Goldilocks epoch that's neither too early nor too late. We necessarily exist within it, because we couldn't exist anywhere else. But that window is closing. Not tomorrow. Not in a million years. We're safe for billions of years more. But eventually, the universe will become uninhabitable and unobservable. The age of structure is temporary. Now, the Great Attractor teaches us something else. It reveals that the universe isn't as unique as we might think. Yes, the Great Attractor is massive. Yes, it pulls on galaxies across hundreds of millions of light years. Yes, it bends the motion of matter on a scale that defies human comprehension. But it's not one of a kind. It's not special. Other basins of attraction exist throughout the universe. The Shapley supercluster sits beyond it, pulling in another direction. The Perseus-Pisces supercluster tugs from a different angle. The Hercules supercluster does the same. They're all comparable in size. They're all comparable in mass, They're all examples of the same cosmic phenomenon. This is crucial. The universe is lumpy on small scales. Galaxies clump together, stars cluster, planets orbit stars, but zoom out far enough, average over regions billions of light years across, and the universe smooths out. It looks roughly the same everywhere you go. This is the cosmological principle, one of our foundational assumptions about reality. If the Great Attractor were a unique anomaly, if our region of space were dramatically different from others, this principle would be shattered. Our models would need a complete overhaul. Instead, the Great Attractor is exactly what the cosmological principle predicts. It's a typical example of the largest structures that gravity can assemble. Its existence fits our theories. Its properties match simulations. Everything about it confirms what we expect in a universe governed by gravity and dark energy, starting from nearly uniform initial conditions. Yet mysteries persist. The structures we observe, the superclusters, the filaments, the vast walls of matter, are slightly larger than our models say they should be. We don't have enough time. The age of the universe since the Big Bang seems barely sufficient for gravity to gather matter into such enormous structures. The math doesn't quite add up. Either something about the early universe was different than we currently model it, or our models themselves need adjustment. The Great Attractor sits right at the edge of theoretical expectations, challenging our understanding while simultaneously confirming it. So what's the ultimate fate of all this cosmic architecture? The answer lies in dark energy, a force we barely understand that's driving the expansion of space itself. If dark energy remains constant, the universe will expand forever. Galaxies will sail apart. Stars will burn out. Matter itself will grow cold and dilute. If dark energy grows stronger with time, expansion accelerates even faster, eventually tearing apart atoms themselves in what cosmologists call a big rip. If dark energy weakens, gravity might eventually overcome it, and the universe could collapse in a big crunch. Current observations favor eternal expansion, but uncertainties remain. The future is written in equations that we still don't fully understand. What we know with certainty is this: the Great Attractor's pull, powerful as it is, will eventually lose its war against dark energy. The expansion of space will win. The universe will keep accelerating outward. The Great Attractor will weaken. The filaments will snap. The superclusters will dissolve. And billions of years from now, the cosmic architecture we see today will exist only in the data we leave behind. A record of structures that once were, but no longer remain. We are the universe observing itself during its age of structure, and that age is temporary. The cosmic frontier, where our maps end and mystery begins. Imagine standing at the edge of everything we know. Behind us lies a billion light years of cosmic architecture. Galaxies mapped, their flows traced, their gravitational dance understood. Ahead of us, darkness. Not the peaceful kind, the unsettling kind. Because here's the truth: we've barely scratched the surface of the universe. For decades, astronomers have hunted for the source of a gravitational anomaly so powerful it's pulling our entire galaxy sideways. They call it the Great Attractor. After mapping millions of galaxies, after untangling the cosmic web itself, we've finally found it. We know where it lurks, We know what creates its pull. We know it's part of something far, far larger. A hierarchy of structures that stretches across scales our minds can barely fathom. But here's where it gets unsettling. The deeper we look, the more we realize how much we're missing. 1/5 of the entire sky is hidden from us. A vast zone of avoidance. A region where the densest cosmic dust creates an impenetrable curtain. Imagine trying to see a city at night, but a thick fog blocks your view of everything except the brightest lights. That's what we're dealing with. Radio telescopes and infrared observations have pierced this veil, but only partially. The dust is too thick. The foreground stars are too bright. They drown out the faint whispers of distant galaxies hiding behind them. We've found major structures like the Norma cluster, but we know with absolute certainty that smaller, perhaps equally important structures remain completely invisible to us. We've drawn the outline, but we're missing the details. Push further out, beyond 1 billion light years, and our maps don't just become incomplete, they become almost useless. Oh, we can detect galaxies out there. We can measure their approximate positions, but that's where our powers of observation crumble. The techniques we use to measure distances fail when galaxies are faint and far away. Cosmic expansion warps their light so severely that we can't determine how fast they're actually moving. We see them, yes, but we can't truly understand them. There's another problem haunting us. The northern hemisphere is swimming in telescopes. That's where the observatories are built. That's where the funding flows. But the southern sky, it's been neglected, and that neglect is costing us. Hidden in the southern sky sits the South Pole Wall, a structure so massive it rivals anything we've found in the north. It remained unknown for centuries simply because fewer eyes were looking that way. Now, as new observatories come online in the southern hemisphere, we're finally beginning to see what we've been missing all along. Yet even with better instruments, there's something far more troubling we can't see at all. Dark matter. It's invisible. Completely invisible. And it makes up most of the universe's mass. We know dark matter forms halos around galaxies. We know it creates the gravitational scaffolding that holds visible structures together. But we cannot observe it directly. Every single measurement we make is a guess, an inference pulled from watching how gravity bends light from distant galaxies, or how visible matter moves under invisible hands. These measurements are crude. The uncertainties are massive. We have a rough picture, like a child's pencil sketch, of where dark matter concentrates. But the true architecture? That remains locked away from us. The cosmic mysteries don't stop there. Take Laniakea, the supercluster that contains our own Milky Way. Is it truly a separate structure falling toward the Shapley supercluster? Or is it actually part of something even larger? A sub-basin within Shapley's gravitational domain. Different scientists using different methods arrive at different answers. The question sounds abstract, but it's not. It determines how we understand the entire hierarchy of cosmic structure, how we define what a supercluster even is, and we still don't have enough data to settle it. Then there's the deepest mystery of all. The largest structures themselves shouldn't exist. The Great Wall, the Sloan Great Wall, the South Pole Wall. They're all catastrophically, impossibly large. According to our models, there hasn't been enough time since the Big Bang for gravity alone to assemble structures this vast. The math doesn't work. Either the initial seeds of matter were far larger than we thought, or cosmic structure forms faster than our theories predict. Or there's a mechanism we haven't discovered yet. Something that efficiently concentrates matter in ways gravity alone cannot explain. The observations are solid. These structures are absolutely real. The mystery is absolute. We stand at the frontier of human knowledge, instruments in hand, looking into an abyss that stares back. We've mapped 1 billion light years, traced cosmic flows, pieced together the universe's grand design. And yet, with each answer we find, 10 new questions emerge. The universe is vast beyond comprehension, and we've only begun to map it. Imagine looking out at the cosmos and realizing that everything you think you know about the universe's fate might be wrong. Dark energy is the culprit. We know it exists. We know it's accelerating the expansion of the universe. We know that one day, billions of years from now, it will overcome gravity entirely and rip apart every galaxy, every star, every atom in the cosmos. But here's the problem. We have no idea what it actually is. We don't know where it comes from. We don't know why it has the precise value it does. We don't even know if it's constant. If dark energy is changing, evolving, shifting over time, then every prediction we've made about the universe's ultimate fate could be completely wrong. The Great Attractor might maintain its influence far longer than we expect, or it might lose its grip on the cosmos faster. Galaxies might cluster into monstrous structures we haven't imagined, or they might scatter and disperse in ways our models can't foresee. Everything hinges on this single mystery: understanding dark energy. But we're not giving up. The next generation of telescopes is coming, and they're going to transform our view of reality. The Vera Rubin Observatory will photograph the entire southern sky every few nights, capturing billions of galaxies and watching how their positions shift across time. The Euclid Space Telescope will map the positions and shapes of galaxies across vast swathes of the sky, measuring gravitational lensing to reveal where dark matter lurks in the cosmic web. The Nancy Grace Roman Space Telescope will peer deep into cosmic history, tracing the large-scale structure of the universe as it was billions of years ago. Each mission will discover new structures. Each one will reveal hidden patterns. Each one will raise more questions than it answers. But here's what they won't be able to do: see everything. There's a zone on the cosmic map that will always remain hidden from us. The densest clouds of galactic dust block certain wavelengths of light completely. They simply cannot penetrate. And beyond our cosmic horizon, there are regions so distant that their light hasn't reached us yet. It never will. We will never see them. The universe is bigger than we can observe. It's more complex than we can map. It's more mysterious than we can ever fully understand. And perhaps that's exactly how it should be. The Great Attractor has been pulling us across the cosmos for billions of years. It shaped our galaxy's trajectory through space. It determined where we're going. It influenced our cosmic destiny. And we didn't even know it existed until decades ago. Now we study it. We map it. We try to understand it. We've learned so much, but the mysteries only deepen. We are explorers in a cosmic ocean. We're charting waters we can barely see. We're following currents we don't fully understand. We're being pulled by forces we cannot resist. The Great Attractor is real. Its influence is real. But 20% of the sky remains unseen. Billions of light years remain unmapped. The universe's largest structures still challenge our theories. Dark matter and dark energy remain enigmas locked away in the darkness. The journey continues. The questions multiply. And somewhere out there, beyond the edge of our current knowledge, wonders wait to be discovered. Perhaps the greatest mysteries don't lie in what we've already found. They lie in what we haven't yet discovered in the vast, unexplored darkness that stretches beyond our reach.